Let's take a journey to a world so distant and alien that it would be unrecognizable even if we peered with all our might. We are going to a place where not a single flower grew, where not a single fish swam in the oceans, and where the outlines of the continents would be completely unrecognizable to us. It was a planet shrouded in toxic air, where life itself was only a timid, barely perceptible whisper, just beginning to emerge from the primordial mud. Let's fast forward 3 billion years into the past. Earth at that time wasn't just young, it was frantic, turbulent, and constantly changing. A planet that was simultaneously deafeningly quiet and chaotically alive. Imagine the combination. It was long before any era we can imagine. There were no mammals here, no birds singing in the branches which didn't even exist. Not even the familiar buzz of insects could be heard. In this deafening silence, only the voices of the planet itself could be heard. The rumble of volcanoes and the roar of ocean waves, ancient seas, clouds of toxic gases, and something else, something incredibly tiny yet full of determination, something that was preparing a quiet but grandiose revolution. Life, in its most primitive microscopic form, was already desperately clinging to this world, enduring the most unimaginable trials. To understand this era, we must travel back so far that the Egyptian pyramids and even ice ages will seem like yesterday. There are no roads and the weather can change in minutes, turning into a death trap. Yet, every summer, geologists hike across glacial plains, traversing miles of icy silence to touch these ancient stones. Some of them return with tiny pieces of banded iron. Others hunt for microscopic grains of graphite. The carbon trapped in these samples may or may not be biological in origin. The samples are tiny, and the journey to them is incredibly difficult and dangerous, but they continue on their way. After all, if this graphite turns out to be biological, it will be one of the earliest indications of life on Earth. But even if it turns out to be inorganic, we will have learned something equally important. It will mean that some carbon signals we thought were sure signs of life may actually be misleading. Such a discovery will force us to re-examine and refine all the tools we use to search for biological traces in the depths of time. This isn't a failure, it's a rigorous test, and its results have implications far beyond our planet. As we hone our tools for studying ancient cataclysms on Earth, we are simultaneously developing technologies that will one day allow us to search for life on Mars, on icy Europa, and on exoplanets orbiting distant stars tens of light years away. Techniques for analyzing sulfur isotopes, studying oxidation-sensitive metals, and imaging microfossils are the same arsenal we will deploy into space to understand whether life is possible elsewhere. That life on Earth nearly destroyed itself, a victim of its own resounding success? These questions take us beyond pure science, acquiring philosophical implications. They urge us to view ourselves not as masters of the Earth, but as its latest, perhaps most risky, experiment. They force us to consider how fragile the balance of nature can be and how powerful creatures can be, discerned only under a microscope or in a slice of ancient stone. These discoveries have the potential to revolutionize our worldview. After all, as scientists say, it wasn't just the existence of oxygen that was discovered, the free will of life itself was revealed. We learned that life is capable of transforming entire planets, These microbes were able to trigger a chain reaction on a planetary scale. Cells too tiny to be seen were able to change the color of the ocean, the composition of the air, and even the very course of geological history. This may be the most astonishing discovery of all. We haven't simply found evidence of the distant past. We found a mirror. To understand the Great Oxygenation Event or any other ancient mystery of Earth, we must come to terms with the idea that we will never see the whole picture. This work requires humility and a willingness to accept that any new discovery could upend everything. It requires reflection, not arrogance. You assemble the fragments, build models, and wait for the stone to decide to speak to you. And yet, despite this eternal wait, something changes within people themselves. Those who dedicate their lives to studying the planet's long memory begin to perceive time in a new way, not as a straight line stretching into the past, but as a boundless landscape, not as something rushing past, but as a space through which they themselves pass, slowly, consciously, like archaeologists exploring the invisible architecture of eternity. This mindset gives birth to new types of scientists. Some become detectives, obsessed with the smallest details. A sharp jump in the isotope ratio, a chemical residue trapped in a quartz crystal, all these become crucial clues in an investigation spanning billions of years. Others become poets, inspired by the beauty of great cycles and the interactions of gas and rock, life and death. And some, perhaps the majority, become pilgrims. They return again and again to the same places, to the same ancient rocks, not because they expect surprises, but because they know that even after millennia, the Earth still holds its greatest secrets. One such place, sacred to Earth historians, is the Gunflint iron ore deposit on the shores of Lake Superior in Canada. Here, in the smallest grains of rock, researchers have discovered some of the most beautifully preserved microfossils, dating back over 1.9 billion years. These tiny filamentous organisms, some coiled, others huddled in tight groups, were captured in the rock with photographic precision. So, in a sense, these geologists, paleobiologists, and isotopic chemists aren't simply telling the story of Earth. They're writing the introduction to a much grander cosmic saga. But great discoveries aren't only made in the field, among rocks and ice. Some of the most stunning breakthroughs occur in the quiet of laboratories, university classrooms, and offices, where enormous data sets are transformed into sophisticated models and computer simulations. It's modeling that allows us to see movement where previously there were only static assumptions. For example, Noah Planovsky's research has forced us to completely rethink the timeline of the planet's oxygenation. He used cutting-edge instruments, measuring the contents of elements like chromium and uranium in ancient sediments, to reconstruct how oxygen spread throughout the oceans and atmosphere. His work showed that low oxygen levels may have persisted for much longer than previously thought. This means that the oxygen revolution was not a sudden explosion, but a long, uneven, and arduous process. Other scientists, such as David Catling, have developed planetary models that describe the delicate balance between volcanic emissions and the burial of organic matter in the Earth's crust. Organic and oxidative scientists are finding common ground between biology and geology, uncovering dynamic cycles of evolution. 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 . 」 In turn, climate and planetary scientists are feeding their findings into global data networks, enriching our shared understanding. Together, they create not just a single coherent story, but a fractal web of possibilities. Theories overlap, collide, and intertwine until a clearer picture begins to emerge from the chaos. And in this picture, we see that our breathable air, our vibrant oceans, and our stable climate are not the planet's factory settings. They are the result of a balancing process that has lasted billions of years. And this process was not initiated by animals, plants, or even the Earth itself. It was initiated by microbes unaware of the consequences of their actions. The people who made this discovery didn't immediately grasp all its nuances either. They began with uncertainty, with trial and error, with questions that seemed set in stone and unanswerable. In other words, they began with curiosity, and this curiosity has become the foundation that permeates this entire long chain of discoveries. It is what drives scientists to set up camp by a frozen river to reach the right outcrop. It drives lab technicians to run the same isotope test 20 times in a row in pursuit of an accuracy that others would consider insignificant. It inspires theorists to model oxygen concentrations on imaginary planets to understand what life might look like if we encounter it in space. And this isn't just about academic achievement. It's about questions that concern our very existence. If breathable air on Earth arose as a result of a random environmental change caused by life itself, what does that tell us about us? What will happen when life, in our form, reaches a new level of power? When will Earth's history become geological again? When will humanity, with its carbon emissions and wholesale environmental change, begin to leave the same indelible marks on the atmosphere as ancient bacteria left iron streaks in rock? Remarkably, the story of the Great Oxidation Event looks to the future as much as it does to the past. It teaches us that feedback is profoundly important, that small changes can accumulate, that the atmosphere reacts to them, and that certain thresholds, once crossed, cannot always be reversed. That's why these scientists continue their work. They return to ancient rocks of the Pilbara, the Gunflint, to deep cores from Russia, China, and Wyoming. They're not simply studying the past. They're learning to see the present clearly, with understanding and humility, with awe and the realization that the most powerful forces in Earth's history have never been the loudest. On the contrary, they've always been the quietest. Microbes, sediments, the planet's slow breathing, and now us. Here they are, the most influential players on this stage. To the average person, a rock is just a rock. But for those who speak the language of Earth's chemistry, that same rock is a veritable book. A keeper of time, filled with the molecular echoes of events waiting to be heard. When we study our planet's distant past, especially events as momentous as the emergence of oxygen, chemistry becomes more than just a science. It becomes a language spoken by isotopes and elements, moving and combining like actors in a slow-motion film spanning billions of years. This is where our journey becomes more technical, but no less fascinating. For hidden within the depths of geochemistry lies a history as beautiful and fragile as the fossils it preserves. And if we delve deeply enough, we begin to understand not only what happened, but how, and sometimes even why. Let's start with sulfur. Of all the elements that tell the story of the Great Oxidation Event, sulfur is perhaps the most eloquent. Not because it's abundant, but because its character changes dramatically depending on the surrounding conditions. In a world without oxygen, sulfur circulated around the planet, leaving behind completely unique isotopic signatures. Scientists call one such signature mass-independent fractionation. In simple terms, in most chemical reactions, isotopes behave predictably depending on their mass. Heavier ones move more slowly and react slightly differently. However, in Earth's early oxygen-free atmosphere, the sun's harsh ultraviolet radiation could break down sulfur molecules in completely unusual ways that defied these rules. This created unique chemical signatures that today serve as an unmistakable marker of that distant era. Let's fast forward to the distant past, billions of years ago, when our planet was a completely alien world. In the oldest rocks from that time, scientists are discovering mysterious chemical fingerprints, completely anomalous ratios of sulfur isotopes. These strange signals, like ghosts from the past, are found everywhere in the rocks of the Archean eon. And these stone records tell us an incredible story. They are irrefutable evidence that the early Earth's atmosphere contained virtually no oxygen. This means the planet lacked the life-saving ozone layer that today protects all life from the sun's harmful ultraviolet rays. And then, approximately 2.5 billion years ago, something monumental happened. These mysterious sulfur signals vanished. Geologically, it happened almost instantly, as if someone had flipped a giant switch. The leading explanation for this tectonic shift is a sharp rise in atmospheric oxygen levels, which in turn led to the formation of ozone. Hard ultraviolet light could no longer penetrate to the surface, and the unusual chemical reactions with sulfur ceased forever. This sudden disappearance of the sulfur anomaly is one of the most striking markers indicating the beginning of the Great Oxidation Event. It doesn't simply tell us about the appearance of oxygen, it marks the moment when our planet's very sky changed beyond recognition. But the story of sulfur is just one chapter in this grand saga. Another key element, without which the picture would be incomplete, enters the picture: carbon. It plays a crucial role in the grand drama of oxygen accumulation. Imagine a global carbon cycle in which the burial of organic matter is a key process. When tiny photosynthetic organisms like cyanobacteria convert sunlight into energy, they release oxygen as a byproduct. But there's a catch. If these organics simply decompose after they die, all the oxygen they produce is immediately reabsorbed. Only when this dead biomass was securely buried under layers of sediment did oxygen have a chance to escape and remain forever in the atmosphere. This mechanism, which geologists call carbon sequestration efficiency, has become the subject of intense study. If the ancient oceans buried more carbon than they could process, the atmosphere became enriched with oxygen. If not, the oxygen remained in a perpetual cycle, unable to accumulate. The ratio of carbon-12 to carbon-13 isotopes in ancient rocks allows scientists, like detectives, to reconstruct this picture. They can determine what proportion of organic matter was buried and what was released back into the system. And here's the interesting thing. In the periods following the Great Oxidation Event, we observe colossal jumps in this ratio. These peaks signal an explosive growth of biomass, its mass burial, and consequently, the possible accumulation of even more oxygen. However, this is only part of the overall puzzle. To know precisely when these events occurred, to put all the biogeochemical shifts in their proper place, we need specialized tools. This is where radiometric dating comes in, a method that allows scientists to assign absolute dates to the geological formations we're discussing. These are no longer just guesses like before or after, but specific time markers. 2.45 billion years ago, 1.88 billion years ago, 7 and 20 million years ago. The most reliable method for dating the oldest rocks is considered to be uranium-lead analysis, which is most often applied to zircon crystals. Imagine zircon, an incredibly resilient mineral, a true time capsule. It can withstand monstrous temperatures, colossal pressures, and millions of years of erosion. At the moment of its formation, it readily accepts uranium atoms into its crystal lattice, but completely rejects lead. And since uranium predictably and slowly decays over time, turning into lead, the ratio of these two elements within the crystal acts as a flawless atomic chronometer. These natural clocks, scattered throughout the world, allow us to peer into our planet's distant past with astonishing accuracy. Without them, all of history would be a collection of disparate and contradictory facts. With their help, we can confidently say exactly when oxygen levels soared and when the great glaciations began. Then, another science comes to the forefront, adding incredible depth to our knowledge: paleobiology. Its practitioners study the remains of ancient organisms, but they are interested in more than just the form of fossils. They seek to understand the ecology, behavior, and even chemistry of these creatures. They study stromatolites, fossilized microbial communities. In an attempt to unravel their structure, they analyze cell wall remnants for so-called lipid biomarkers and search for preserved microbial structures in carbonate rocks and shales. One of their most powerful tools is microspectroscopy, which allows them to scan tiny fossils for molecular compounds. For example, certain lipids, like 2-methylhopane, are directly associated with cyanobacteria. Their presence in the rock is direct evidence that photosynthesis occurred here billions of years ago. Another amazing tool, scanning electron microscopy, allows us to see fossil cell walls in exquisite detail. This allows us to understand what these microbes were like, whether they reduced sulfur, produced oxygen, or did something else. Nitrogen isotope analysis, in turn, helps reconstruct nutrient cycling. Was nitrogen available to life? How much of it was there? These data allow paleobiologists not only to confirm the existence of life, but also to understand what it was like and how it interacted with its world. And here it becomes clear, none of these signals can be viewed in isolation. Scientists are combining data on sulfur, carbon, nitrogen, uranium, and fossils to create a unified, coherent picture. They are like artists blending individual brushstrokes to create a new, meaningful figure on the canvas. And that figure is a map of early Earth. But even with this approach, something is missing. To truly understand the past, it's not enough to know what happened. It's important to understand how exactly it happened. This is where climate modeling comes in. Modern researchers create digital models of the ancient Earth, taking into account variables such as the activity of the young sun, greenhouse gas concentrations, the reflectivity of ice caps, and even the circulation patterns of ocean currents. These models are highly complex simulations that are then verified against real geological data. For example, one model clearly demonstrates how even a slight increase in oxygen could have led to the collapse of methane in the atmosphere, which in turn caused a sharp global cooling. Another model examines how the breakup of ancient supercontinents affected the supply of nutrients to the ocean, triggering a rapid growth of photosynthetic microbes and further oxygenation of the planet. These models are not perfect, but they are constantly improving, especially with the advent of machine learning, which can detect patterns in complex climate systems that were previously invisible to the human eye. Let us plunge into the dense mists of prehistoric times, to an era when the sun shone much less brightly, the days on the planet were shorter, and the oceans held countless secrets in their dark depths. We are not simply traveling back in time. We are traveling to an entirely different planet to see it as it was in its wild youth. Sometimes great stories begin not with grand events, but with small but mysterious clues. These clues may seem insignificant, like a compass needle that suddenly and inexplicably veers off course, or like a silent cliff somewhere in the Australian desert whose red rocks seem to hold memories of a past we've long forgotten. Our modern world is full of such echoes, subtle hints of grand dramas played out in the depths of antiquity. Take, for example, a sun-baked swathe of land in Western Australia, known to geologists as the Pilbara Craton. At first glance, it's a lifeless wasteland, just dry rocks and sparse thorny shrubs beneath a merciless sky. But look closely at the layers of these ancient rocks, and you'll discover something incredible. Hidden within them are tiny fossilized structures, the imprints of ancient microbes, so old that dinosaurs seem like visitors from the distant future in comparison. Some of these fossils are nearly 3.5 billion years old, making them among the oldest direct evidence of life ever found. Now let's move on to South Africa. The combination of geochemistry, radiometric dating, paleobiology, and climate modeling opens up entirely new horizons. Scientists don't have a single answer to every question. Instead, they present us with a spectrum of possibilities, a space of plausible scenarios. It's like a cloud of memories, fuzzy at the edges but becoming increasingly clear and distinct in the center. And through this cloud, another far more important question emerges. If the oxygenation of Earth was caused by life, and that life completely transformed the entire planet, could something similar have happened in other corners of the universe? This is where astrobiology, the science at the intersection of astronomy, biology, and geology, is taking its first bold steps. Astrobiologists are taking lessons learned from Earth's past and projecting them onto other worlds. They ask, what would the Great Oxidation Event have looked like on some distant exoplanet? Would we be able to detect its chemical signatures with our telescopes? Will we ever see another world in the midst of its great transformation? Its oceans rusting with oxygen, its skies changing color, its life creating an entirely new atmosphere. Some future space missions such as the LUVOIR and HABEX telescopes are aimed precisely at solving these grandiose problems. They will allow us to search for oxygen, methane, and other biologically active gases in the atmospheres of distant planets. We are not looking for life itself, but for its chemical echo, its imprint left on the environment. We are searching for the breath of life. Thus, the Great Oxidation Event ceases to be simply a chapter in Earth's history. It becomes a universal pattern, a kind of cosmic blueprint, a story that may be unfolding right now in the stillness and cold of another star system, where a tiny blue-green dot is just learning to breathe. The deeper we delve into our planet's past, the more clearly we see it as a series of subtle and dynamic balancing acts, measured not in years, but in eons. The oxygen surge was one of those rare planetary moments when the scales tipped and never returned. But even today, our planet is still adapting, still reacting to that ancient event. Ancient processes such as the carbon, nitrogen, and water cycles continue to link mountain weathering with ocean alkalinity, maintaining the delicate balance of life. To truly understand our world, we must recognize one simple truth. Stability is an illusion. Our planet is not a monument frozen in time, but a complex living mechanism. Imagine a colossal system of gears and levers where everything is in perpetual motion, where the slightest change in one part triggers a response in another, and powerful blows of fate set the entire structure in motion. To understand these ancient processes, dry numbers are not enough. They also require a philosophical perspective on the very nature of things. Let's travel back in time and look at one of the greatest climate regulators, the weathering of silicate rocks. It sounds complicated, but it's essentially a brilliant planetary thermostat. When rainwater, saturated with carbon dioxide, washes over rocks, it engages in a slow chemical war with the rock. Drop by drop, year after year, it dissolves the rock, creating so-called bicarbonate ions. These ions are carried by rivers to the ocean, where they eventually become part of carbonate minerals, permanently locking the carbon in rock sediments at the bottom. Most interestingly, the speed of this reaction is directly related to temperature. The warmer the planet, the more active the rains and chemical processes, and therefore the faster carbon dioxide is removed from the atmosphere. This is how Earth cools itself. Over entire geological eons, our planet evolved, refining this mechanism. Scientists, using sophisticated computer models, were able to peer into the past and see how this system operated during the Great Oxidation Event. When methane in the atmosphere began to give way to carbon dioxide, it was the weathering of silicates that likely began to slowly but inexorably reduce CO2 concentrations, pushing the world toward global cooling. This trend ultimately led the planet to the monstrous Huronian glaciation. But the pendulum swings both ways. When continents are covered in ice or tectonic activity ceases, the weathering process slows dramatically. Then, carbon dioxide, emitted by volcanoes, begins to accumulate in the atmosphere again. The planet warms, glaciers retreat, and the ice age comes to an end. This great rhythm, this alternation of inhalations and exhalations stretching over millions of years, is the very breath of the Earth, slow, barely noticeable, but absolutely essential to sustaining life. However, the rock isn't the only player in this climate drama. There's another, no less powerful force at work: the biological pump. Life in the ocean is a gigantic conveyor belt for carbon processing. Microscopic phytoplankton in the sunlit upper layers of the water, like forests on land, greedily absorb carbon dioxide through photosynthesis, converting it into organic matter. This process is one of the pillars that maintains atmospheric stability. When these tiny organisms die, their final great journey begins. Their remains, like endless organic snow, slowly sink through the dark waters. If they aren't eaten or decompose along the way, the carbon locked within their bodies will be buried on the ocean floor, locked out of circulation for millions of years. In the Proterozoic era, with the emergence of more complex eukaryotic cells, this pump kicked into high gear. Multicellular life emerged as one of the most powerful climate regulators on the planet. Modeling shows that even minor changes in the efficiency of this living conveyor belt can cause colossal fluctuations in atmospheric CO2 levels, even without volcanoes or weathering. Biology often provides us with keys to understanding the most complex processes of the past. Take, for example, the concept of ocean restratification. This scientific term conceals a dramatic picture of the world that emerged after the oxygen catastrophe. For over 1 billion years, the Earth's oceans were structured like a layer cake. At the surface, where photosynthetic organisms lived, the water was saturated with oxygen. But deeper, another realm began, anoxic, and sometimes toxic, waters oversaturated with hydrogen sulfide or iron ions. These chemical boundaries were insurmountable barriers that dictated evolution's course. They determined what types of metabolism could exist, what nutrients were available, and what toxins would accumulate in a given zone. Geochemists have learned to decipher the history of these ancient oceans using trace elements such as molybdenum, vanadium, and chromium. Their behavior is directly dependent on oxygen conditions. By analyzing the concentrations of these elements in ancient sedimentary rocks, scientists have been able to reconstruct a picture of a chemically diverse, stratified, and highly unstable world ocean. All of this brings us to one of the most exciting areas of modern science: Earth systems modeling. Here, in virtual space, geology, chemistry, biology, and climatology are woven together to paint a complete picture of our planet's evolution. Researchers are creating complex, interconnected models to understand how one event leads to another. What happens if a cyanobacteria explosion occurs in a closed body of water? How will increasing phosphorus in the ocean affect the overall productivity of life? Will oxygen accumulate in the atmosphere if the water still contains too much free iron? These questions are more than just scientific curiosity. They help us understand how fragile or conversely resilient the ancient world was. Models show, for example, that atmospheric oxygenation was not a smooth process. Rather, it was a series of pulses, short bursts, that could have been triggered by random events, a sudden influx of nutrients due to tectonic shifts or shifts in ocean currents. These false dawns likely occurred many times before the system finally crossed the fatal threshold. It's this concept, the threshold or point of no return, that's key. The fundamental idea is that Earth can exist for millions of years in a seemingly stable state, and then, due to a single watershed event, the entire system can be radically and irreversibly restructured. This isn't chaos, it's simply a different kind of order, where seemingly insignificant changes ultimately lead to monumental consequences. Today, we call such moments Earth system transitions, and the Great Oxidation Event was one of the first and most dramatic. Later, there were others. For example, the snowball Earth episodes of cryogenics, when the planet was almost completely covered in ice, or the famous Cambrian explosion, when the complexity of life and food chains increased exponentially. And perhaps, right now, in our era, we stand on the threshold of a new great transition, this time caused not by microbes, but by ourselves. When we delve into Earth's deep history, a sobering realization dawns. Nothing on this planet is eternal or guaranteed. Not the composition of the atmosphere, not the chemistry of the oceans, not even the familiar cycle of seasons. All of these have changed in the past, and they can change again. This understanding has completely revolutionized the earth sciences. There are no longer isolated disciplines. Today, scientists work at the intersection of geology, biology, and chemistry, creating climate models and analyzing isotopic data to gain a holistic picture of the planetary machine. With this came a new worldview. The idea of the anthroposphere, the layer of Earth dominated by human activity, isn't just philosophy. It's a real geochemical fact, measurable by our carbon emissions and the way we've altered the nitrogen and phosphorus cycles. We're not just passive observers. We've become an active geological force. And in this strange, closed symmetry of history, we're repeating the path of the ancient cyanobacteria, inadvertently altering the composition of the atmosphere, testing ancient equilibrium mechanisms, and triggering chain reactions we barely understand. However, unlike those ancient microbes, we have something they didn't: the ability to look back. We have science, models, rock samples, and fossils. We can read history written in stone and encoded in isotopes. We can see not only what exists now, but also where our actions might lead. Perhaps the most important lesson of the Great Oxidation Event is not a lesson about oxygen, but about transformation. It's about how complexity emerges from simplicity and the devastating power of the smallest things. And this lesson is addressed to us, those who are willing to listen, who are able to piece together a complete picture from fragments, and who sense the changes in the air. Earth science isn't just the study of the past. It's the art of listening to our planet. And if we are patient and humble enough, we might hear what she's been trying to tell us all along. Life is powerful. Change is inevitable, and balance is but a fleeting moment in eternity. Even after billions of years, having endured mass extinctions, ice ages, and volcanic firestorms, this planet remembers everything. When the world changed forever, it didn't happen with much fanfare. There was no blinding flash, no single dramatic moment. The day the sky turned blue and the air breathable was just one of countless days in Earth's slow, drawn-out history. The oxygenation of the atmosphere was a painfully long, uneven process, with setbacks and leaps forward. The consequences of this revolution came even more slowly. What began was not so much creation as restructuring, and it took hundreds of millions of years. At first, the effects of oxygen's arrival were barely noticeable. The countless life forms that had thrived on the old oxygen-free world, anaerobic bacteria, archaea, entire microbial civilizations, began their retreat. They were driven to the planet's outskirts. They didn't disappear completely, but the center stage of life was no longer theirs. These ancient rulers of the world became exiles, finding refuge in deep seabed sediments, in sulfurous hydrothermal vents, anywhere out of reach of this new deadly gas. Let's fast forward to those distant times when ancient life still clung to existence in extreme conditions, such as dry salt lakes and deserts. There, on these harsh worlds, it still preserves its archaic metabolic secrets. But just above them, at the very surface of the primeval oceans, a true drama unfolded, one that would change the planet forever. With the advent of oxygen, the appearance of the aquatic world began to transform. Iron, once abundant and easily absorbed by organisms, began to rapidly disappear. Reacting with oxygen, it turned into common rust and settled in gigantic layers to the seafloor, forming massive reddish deposits. Sulfides were oxidized, methane reserves were depleted, and along with them, many other chemical compounds that fueled the earliest forms of metabolism vanished into oblivion. However, this great chemical revolution opened the way to an entirely new biochemical world. Free oxygen, albeit in microscopic doses but uniformly distributed in water, became the key to an incredible breakthrough. This led to the emergence of aerobic or oxygen-based respiration, an energy source that was nearly 20 times more efficient than its anoxic predecessors. Imagine your engine suddenly becoming 20 times more powerful while consuming the same amount of fuel. Cells suddenly gained the ability to extract colossal amounts of energy from the same amount of food. They could grow faster, store more genetic information, and develop complex internal structures. This set the stage for the greatest achievement of all, the emergence of eukaryotes. These were cells with internal membranes, veritable microscopic cities with their own organelle-like quarters and a central city hall-like nucleus. The earliest fossil evidence of their existence appears in the geological record shortly after the Great Oxidation Event, although they likely evolved much earlier, lurking in the chemical darkness of the ancient world. Here, the Barberton Greenstone Belt unfolds before us like an ancient, decayed manuscript. Every fold, every crack in these rocks is a new chapter in the annals of our planet's early history. Here, under the blazing sun, geologists chip away at chunks of rock formed when the Earth's crust was still young and unruly. The minerals they find tell stories of ancient seas, violent volcanism, and microscopic life just beginning to take its first steps. These places don't shout about their past, they whisper. And the scientists who work here, geobiologists, geochemists, field researchers with sun-bleached notebooks, act as decoders. They understand the language of isotopes, decipher the structures of sedimentary rocks, and can decipher the ancient stories these stones have preserved for billions of years. The molecular traces left in the rock help them recreate a world we can never see with our own eyes, but can still try to understand. One such scientist, William Schopf, made a startling discovery in the 1980s. Peering through a microscope, he saw fine hair-like filaments in a sample of ancient rock. Their shape was strikingly similar to modern cyanobacteria. The scientific community initially greeted his claim with skepticism. Many believed them to be mere bizarre mineral formations, a freak of nature. However, as the years passed, new, more sophisticated analytical methods emerged: Raman spectroscopy, isotope analysis, scanning electron microscopy. In between lay an unstable zone where a strange, bizarre metabolism still took place. Nevertheless, the planet's surface was changing. The Proterozoic period, sometimes referred to by paleontologists as the boring billion, was anything but boring. It was an era of quiet behind-the-scenes work, of slow but steady progress. Evolution made no leaps. It proceeded by trial and error, patiently experimenting across countless genetic lineages. Some organisms learned to form colonies, others primitive tissues. Cooperation became a winning strategy, and cellular specialization was the dominant theme of the era. And so, at the end of the Proterozoic, about 600 million years ago, the first true animals began to appear on the planet, creatures with soft, often pliable bodies. Their traces in the rock record are mere ghostly imprints, fragile and incredibly rare. But they indicate that the biosphere was preparing for a massive expansion. Oxygen levels, though still far from today's, had become stable enough to support organisms with a much higher energy appetite. And then, as if the Earth froze. About 720 million years ago, the planet plunged into a deep, icy sleep known as the Cryogenian period. At least 2 global glaciations occurred, events so extreme that they are known as the snowball Earth hypothesis. A kilometer-thick ice shell encased the continents and oceans, reaching all the way to the equator and reflecting precious sunlight back into space. Perhaps the entire ocean froze to the bottom, leaving only tiny refuges of liquid water near geothermal vents or under a thin layer of equatorial ice. Life endured the most brutal ordeal, but did not disappear. It adapted, hid in the last oases of warmth, and continued its slow evolution. Organisms not only survived, they may even have hardened in this icy hell. These glaciations acted as evolutionary filters, weeding out the weak and fostering resilience and versatility in the surviving life forms. When the ice finally retreated, likely due to colossal emissions of volcanic carbon dioxide, which had accumulated under the ice crust for millions of years, the Earth became a giant greenhouse. Oxygen became available again, and the oceans refilled with nutrients washed out by the melting glaciers. And life responded enthusiastically to these changes. The Ice Age was followed by the Ediacaran period, marked by the appearance of the first large and complex organisms. A wondrous garden of strange creatures blossomed on the seafloor. Some resembled giant fern fronds. Others resembled quilted oval mattresses spread out on the mud. Some may have crawled slowly along the bottom, scraping away microbial mats, while others were sedentary. These creatures weren't yet animals as we understand them, but they represented something entirely new. Nature's first great experiment in creating multicellular organized communities. They formed ecosystems, left traces, and grazed. And most astonishingly, they laid the foundation for an event that shook the world, the Cambrian explosion. Around 542 million years ago, as if at the snap of a finger, the fossil record exploded with a diversity of new life forms. During this astonishing period, the first shells appeared, the first eyes to see, the first limbs to move, and the first jaws to grasp. Predators and their prey emerged, and the first coral reefs emerged. The seafloor, once a quiet haven for microbes, became a bustling arena of activity, struggle, and evolutionary innovation. This explosion of life was fueled largely by oxygen. By then, Its concentration in the atmosphere and shallow oceans had reached almost modern levels. Respiration became more efficient, enabling the development of complex nervous systems and muscles. Mobility became the key to prosperity. A veritable ecological arms race began, greatly accelerating the pace of evolution, making it more complex and spreading it across the planet. Everything that appeared later, forests, dinosaurs, mammals, was made possible by this remarkable period. Over long periods of time, atmospheric oxygen levels slowly but surely increased. This was not simply a byproduct of life, but a truly creative force. But the story doesn't end there. As life became increasingly complex, it itself began to shape the planet's oxygen cycle. The giant forests of the Carboniferous period acted as enormous pumps, absorbing carbon dioxide and storing carbon as coal, allowing oxygen to accumulate unimpeded in the atmosphere. Animals, in turn, altered the nutrient cycle. Fungi, decomposing dead wood, returned carbon and nitrogen to the system. The biosphere transformed from a passive consumer into an active regulator. Over the past 500 million years, atmospheric oxygen levels have experienced dramatic peaks and troughs. During the Carboniferous, concentrations may have reached 35%, fueling the emergence of giant insects like eagle-sized dragonflies and igniting the widespread forest fires that raged across the planet. However, during the Permian, oxygen levels plummeted, contributing to the greatest mass extinction in Earth's history. Each of these peaks and troughs was intimately linked to the rhythms of life and geology, shaping the unique and unrepeatable history of our planet. Oxygen, this powerful element, has always been both a great gift and a deadly threat. A shortage could stifle complex life, while an excess could scorch the entire planet. For 500 million years, Earth has balanced on this knife's edge, trying to maintain a delicate balance between the energy for life and safety from fire, between breath and all-consuming flame. We cannot know the future, but the annals of the past provide insight into how long it takes for the planet to heal after great upheavals. We know what happens when the very source of breath disappears from the atmosphere. We have seen how the oceans are transformed when their delicate balance is disrupted. We need only momentarily forget what our planet is capable of to appreciate the value of what we have. And this knowledge has reached us through the ages, recorded in slow and patient chapters carved into the depths of stone. What an incredible miracle it is simply to be alive, to breathe an atmosphere woven not simply from a mixture of gases, but from time itself. To walk on a planet that once had neither the familiar sky nor breath nor a single sound. And now, thanks to the choices made by the most ancient cells, thanks to a chain of incredible chance, complex life has emerged capable of speech and choice. It could become just another short entry in the long list of Earth's catastrophes, or it could finally evolve into a species that has learned to listen to the whispers of the past. What happened 3 billion years ago may seem like science fiction to us, an event from such a distant past that its world is completely unlike our own. Imagine a planet without animals, without flowers, without the slightest sound. No foot has ever set foot on this land. No eye has ever seen its landscapes, open only to the cold light of an ancient sun. And yet, what happened in that primordial silence has not disappeared without a trace. Echoes of those events resound in our lungs, in our thoughts, in every breath we take. We are all the heirs of oxygen, and our very lives are built on this amazing gas. Once a deadly poison for all living things, it eventually became an elixir that allowed complex organisms to emerge. Our energy, our movement, our entire civilization, all are the result of a remarkable chemical coincidence, so colossal that it seems almost mythical. However, it is no myth. It is a memory imprinted in every beat of our hearts. When we reflect on the Great Oxygenation Catastrophe, we go far beyond dry geochemistry. We're studying more than just sulfur isotope ratios or the structure of a corroded seafloor. We're asking questions that are increasingly troubling and at the same time beautiful. What kind of planet is it on which life itself is capable of reshaping its own atmosphere? And what kind of species would it take to dare to replicate this process? This parallel is haunting. Once upon a time, simple microbes, simply by living and reproducing, excreted waste products. And this waste, oxygen, played a key role in shaping our world. It caused mass extinctions, encased the planet in glaciers, and forever altered the chemical composition of the oceans and atmosphere. And now, billions of years later, we see a frightening pattern in this. What if one day another species began producing a different kind of waste? What if carbon became the primary culprit? The mechanisms driving global change may differ, but the outcome remains the same. The atmospheric balance is disrupted, the planetary thermostat malfunctions, and the rules of the game are rewritten. Just as oxygen once poisoned ancient organisms, carbon dioxide and methane are affecting our world today, warming the oceans, acidifying the seas, and eroding centuries-old glaciers. However, there is one colossal difference: speed. Oxygenating the planet was a process that spanned millions of years. The current rise in CO2 emissions, however, is occurring faster than any natural climate fluctuations we've ever recorded in the geological record. It's happening faster than corals can adapt, faster than glaciers can recover, and faster than entire ecosystems can migrate in search of safety. And the consequences of these rapid changes remain a mystery to us. However, this realization doesn't plunge us into despair. On the contrary, it brings astonishing clarity. If a single species of microbe, primitive and ancient, was capable of changing the face of the entire sky, then what is intelligent life, armed with telescopes and satellites, ethics and art, capable of? If bacteria could trigger planetary transformations without even suspecting the existence of the planet itself, then what can we do with this knowledge? It's a sobering look at hope. Not naive, not simple, but honest. Because Earth doesn't need us to survive. It survived the collision of continents. It healed the wounds of its oceans. It watched the stars shift and the composition of its own atmosphere change. Earth will remain here, ever-changing, breathing, adapting. It will be here long after we are gone. But life as we know it, our civilization and culture, are a different matter entirely. The lesson learned 3 billion years ago must not be forgotten. What's important is not just that oxygen changed the world, but also how it happened, slowly, unevenly, and completely unpredictably. The planet experienced dramatic fluctuations, froze in icy torpor, and desperately tried to find a new equilibrium. Entire ecosystems were wiped off the face of the earth, and it took an eternity to recover. This should give us pause. What we're disrupting today may take immeasurably longer to recover, and changes we perceive as reversible, warming, acidification, extinction, may prove to be a point of no return. The Earth is not a machine. It is a living system that operates in rhythms far larger than our political cycles or economic quarters. Once a critical threshold is passed, once a glacier collapses into the sea, a current slows, or a species disappears forever, recovery is not guaranteed. Cycles don't always return to their starting point. Therefore, our responsibility is not to save the Earth, but to respect it. It's important to understand that the atmosphere we live in is the result of processes older than any story we can tell. The balance we enjoy is precious, fluid, and incredibly complex. Life itself is not constant. It is dynamic. And these parallels extend far beyond climate. They touch on issues of technology, scale, and how we measure progress. When we observe how oxygen levels have risen through countless tiny actions, microbe by microbe, changing the chemistry of the world day by day, we understand something profound. This reminds us that global transformation doesn't require malicious intent. It only requires cumulative effect. This is how great change happens, slowly, almost imperceptibly, and then suddenly. We have become this force not through malicious intent, but through our scale, not by choice, but by necessity, by inertia. We have transformed ourselves from passive observers of time into active participants in geological processes. Our cities leave their mark on history. Our plastics find their place in the fossil record. Our emissions alter the isotopic ratios of carbon in the atmosphere and in the bones of living things. And yet, recognizing this, we can choose how to respond. We can draw on humility, imagination, and a kind of wisdom that transcends a single human lifetime. Because Earth has taught us something extraordinary. Fragility and resilience are not opposites. They are partners. The biosphere is a delicate yet remarkably patient organism. Life regenerates, adapts, and experiments. And the evidence continued to accumulate, layer upon layer, like sediment at the bottom of an ancient sea. There was no doubt these were not just minerals. Once upon a time, they had been alive. And it is here, in this moment of awareness, that our wondrous journey begins. Not with thunder and cataclysms, but with the understanding that the Earth was already alive back then. Not as we know it today, without horns, feathers, or juicy fruits, but already within it, an ancient force had been born, one day destined to shape the very sky above us. To understand what this means, we must completely abandon our familiar images. We must imagine Earth not as a blue-green planet with oceans and bustling cities, but as a harsh, alien, and incredibly resilient world. 3 billion years ago, Earth was spinning at breakneck speed. A day here lasted only about 14 hours instead of our 24, and the moon, our eternal companion, was much closer and appeared as a huge disk in the sky, causing monstrous tides that were many times more powerful than today's. The sun was dim and cold, giving off about 30% less light, and its weak rays struggled to penetrate the thick, hazy atmosphere. The air there contained virtually no oxygen as we know it. It was a toxic mixture of nitrogen, carbon dioxide, methane, and ammonia, a composition more suitable for a chemistry lab than a picnic in the park. The continents we know today didn't exist either. Even after the oxygen catastrophe, when Earth plunged into a deep freeze, when entire classes of organisms were lost, something still remained. And from these ashes, something new was born. Life is full of difficulties. It fades, but is often reborn. And perhaps this is the most profound reflection of truth. Life is not a ladder or a pyramid, but a mighty river that branches, divides, returns to its former channel, and always moves forward. And we, with our short and vibrant lives, are only a part of this flow. We are not its peak, we are only a moment in it, and in this moment, we can shape what happens next. We can look to the past not as a place of loss, but as a source of insight. The Great Oxygenation Catastrophe wasn't a tragedy. It was a revelation. Yes, it was brutal, but it opened the way to new possibilities, to energy, to movement, to the future. The challenge is to look to this future while preserving what we have in the present. We must recognize that we live in a state of temporary equilibrium, that our oceans, atmosphere, and biosphere are not static. They are responsive and breathing just like us. There is something sacred in this. This recognition, transcending data and politics, is a kind of planetary grace that we have not earned but inherited, and now must decide how to use it. We could have chosen a different path, listened more, built more slowly, learned from the mistakes and warnings of the past. We could have left behind an atmosphere not untouched, but better understood, because the atmosphere is more than just the sky above. It is a story that began long before us, with tiny cells in silent oceans. It is a story of patience, tension, and endless experimentation, and this story continues within us. Imagine our planet walking a knife's edge. Take one false step away from its sun, and permafrost binds the oceans. Step too close, and the seas boil, turning the world into a scorching desert. This delicate balance was not just important, it was the only condition for the emergence of everything we know. In this ancient world, three great forces, gases, crustal movement, and life itself, were in a perpetual dance. The atmosphere, like a giant lung, inhaled the toxic fumes of volcanoes and exhaled new compounds that became the cradle of the first microbial colonies. The ocean was a veritable chemical cauldron, brimming with minerals that served as building material for some and food for others. Nothing stood still, not even for a moment. Even without forests and bizarre trilobites, the earth pulsated with its own unique, invisible life. And above all this frenetic activity, at the very heart of the planet, its molten iron core thrummed. It generated an invisible but powerful force, a magnetic field. This silent guardian enveloped the earth in an invisible dome, becoming its primary shield. It absorbed the blows of the merciless solar wind, protecting the fragile atmosphere from destruction. It also painted the aurora borealis across the skies, a magnificent spectacle that no one will see for billions of years. It is thanks to this ancient magnetic field that our compasses work today. And within the depths of the most ancient rocks, tiny particles, magnetite crystals, are preserved like compass needles, pointing to the location of the poles in the distant past. Geologists studying the past are like detectives. They reconstruct the world not only from fossilized remains or gas bubbles in ice. They read history from the arrangement of minerals, the different isotopes they contain, and the way geological layers folded and shifted. It's like trying to understand a story told in a language older than any human tongue. And so, when today, in some remote corner of the planet, a compass needle suddenly begins to tremble slightly, deviating from true north, who knows? Perhaps at that moment, we hear the faintest whispers of a time when our world was younger, full of secrets, and bathed in an entirely different, otherworldly light. We're used to thinking of ourselves as the arbiters of the planet's destiny, but the truth is, we're far from the first to change it beyond recognition. We're only the first to recognize this and write our story. Even then, in time immemorial, all the preconditions for the great changes to come were laid. Oxygen levels in the atmosphere were slowly but surely rising. Microbial life, those invisible workers, tirelessly altered the chemical composition of the oceans and the air itself. Tectonic plates, still clumsy and amorphous, had already begun their great journey. They were spreading apart, colliding, diving under each other, raising the first mountain ranges from their depths, and laying the foundation for the future ballet of continents. In those eras, there were no deafening catastrophes or great extinctions, only the leisurely, almost silent development of biology and geology, like a long and intense prelude to a grand symphony. But the curtain was about to rise. The planet, as is its wont, was preparing for its next transformation. Let's travel back 3 billion years, trying to imagine that Earth is a journey into a world woven of rock, chemistry, and deafening silence. There are no familiar maps, no continents, not a single creature capable of surveying this landscape, only shifting flows of lava and water. This world had no face yet, only moods, sometimes furious and molten, sometimes pensive and serene. This was a planet not made for us, but it was already invisibly preparing the ground for our emergence. If we were to find the edge of this ancient coastline, we wouldn't recognize it. Forget about familiar beaches. Here you won't hear the cries of seagulls overhead, and beneath your feet you won't find a scattering of shells washed up by the surf. The land, if you can call it that, is a mass of rising, razor-sharp tongues of black volcanic basalt. They're covered only by a thin crust of minerals and salt, upon which damp carpets of microorganisms glisten faintly, catching the rays of a young sun that was just learning to shine at its full potential. These coastlines, like newborns, still fledgling, rose straight from the boiling oceans, which washed them not with cool water, but with waves of heat and sulfur. The water itself here wasn't clear and azure, but turbid, thick with dissolved minerals, and most likely had a reddish-brown tint like rust. The air was thick with the metallic taste of iron and the subtle chemical, rather than organic, scent of nascent life. With each incoming wave came the whisper of underwater volcanoes and hydrothermal vents. There, in the dark depths, columns of hot metal-rich water gushed from cracks in the crust. They nourished armies of invisible microbes for whom sulfur and iron were not poison, but a veritable feast. These were the waters of an entirely different planet, not yet resembling our hospitable blue world. The sky above would have looked alien to us too, smoky, orange, and at times perhaps even pinkish. It was filled with methane, ammonia, and the heavy breath of volcanoes erupting over millions of years. There were clouds, of course, but they carried acid rain rather than life-giving moisture. The atmosphere shrouded the planet in a dense fog, acting as a giant greenhouse. It protected the surface from deadly ultraviolet radiation, but at the same time retained heat, turning the world into a cauldron of gas and lightning. The land itself was pristine. This world, riven by young tectonic faults, knew neither the rustle of trees in the wind nor the softness of grass underfoot. Only bare rocks, scorched by colossal pressure, sparkled with mineral crystals that could only have formed under the most extreme conditions. Belts of so-called greenstones snaked across the surface like gigantic scars from ancient wounds, frozen in eternity. Regions like the Pilbara in Australia or the Craton in South Africa are the oldest surviving fragments of the Earth's crust. They are veritable time capsules, geological memory imprinted into the rocky skeleton of our planet. If we had found ourselves on this primeval Earth, we would have been deafened by the silence. Not a twitter of birds, not a chirp of insects, not a roar of mammals. Absolute, almost cosmic silence, broken only by the dull, distant rumble of a volcano or the crack of cooling stone. This world was not created for comfort, but it was alive, and life, against all odds, had found a way to establish itself there. The very first life forms were microscopic and solitary. They left behind no bones or paw prints in the mud, but their cumulative impact on the planet was so colossal that it could not be compared to any giant. These ancient microbes huddled in colonies, forming sticky films that clung to rocks, huddled near underwater hot springs, or floated near the ocean's surface, where the light was dim but sufficient for survival. They greedily absorbed chemical elements, released gases, and split molecules with the patience and precision of clockwork. And over time, their barely audible metabolic whisper turned into a deafening roar that transformed the entire planet. Some of them learned to use sulfur in their metabolism, emitting foul-smelling gases that ultimately formed the chemical composition of the ancient oceans. Others adapted to feed on iron or hydrogen, but perhaps the most remarkable were those who invented photosynthesis. Certainly not as complex as that of modern plants, but more ancient and crude, but no less effective. This was the first primitive attempt at turning the world green. Their vital activity began to release oxygen into the environment. These microscopic world builders had no idea what destructive power they carried within them. They didn't understand that they had become true revolutionaries, the instigators of planetary upheaval, but with every ray of sunlight they captured, they altered the composition of the atmosphere, ultimately leading to catastrophe for almost all life that had existed before them. And yet they continued their work. In shallow sunlit seas, microbial mats began to grow on top of each other. Gradually, layer after layer, they compacted, bonded with mineral particles, and formed astonishing stone structures that we today call stromatolites. Imagine a living dome, built not of concrete, but from countless generations of bacteria. Each new layer lived on the remains of the previous one, creating a kind of microbial metropolis that grew over millennia. These formations grew agonizingly slowly, sometimes requiring centuries to add just a few centimeters in height. But they were incredibly resilient, some of them fossilized, leaving us with intricate patterns in ancient limestone rocks, indisputable evidence of life that desperately refused to remain invisible. And today, In several corners of our planet, you can see the living descendants of these ancient builders. One such place is Shark Bay in Western Australia. The water there is so salty that most modern marine predators cannot survive in it, allowing these ancient structures to survive to this day. They are a true window into a world that existed long before the advent of trees, insects, and even complex cells. In those distant times, the Earth's interior was much hotter and more turbulent. The mantle literally boiled with the energy it held, and the crust was thinner and more prone to fractures. Tectonic plates, barely formed, were already drifting, colliding, and creating chains of volcanic islands. These proto-continents, tiny and scattered, bore little resemblance to modern continents. The climate was harsh, and the land was largely barren, constantly shifting due to the chaos raging deep within. Ice caps did not exist. The poles were likely warm, while the equator was cooler. Rain falling from the methane atmosphere turned into a weak acid, which, running down rocks, reacted with minerals, triggering new chemical reactions in the planet's atmosphere. The Earth's surface was completely different. Rivers, if they existed at all, carried dissolved iron to the oceans rather than pure fresh water. Over time, the chemical weathering of rocks caused by acid rain would play a key role in regulating the climate, absorbing carbon dioxide from the atmosphere and balancing it. Thus, the planet's atmosphere became caught in an endless feedback loop between rock, air, and life. Today, this mechanism is known as the carbon-silicon cycle, and it can be compared to a very slow but reliable thermostat for the entire planet, and it began its work 3 billion years ago. At the same time, a process generating a magnetic field was in full swing in the Earth's liquid outer core. Although weaker than today, it was powerful enough to repel the most violent gusts of the solar wind. This invisible shield kept the atmosphere in place, preventing it from being blown into outer space. There was a force, an invisible guardian, silent and absolutely essential for nascent life. This hero was the Earth's magnetic field. Without this invisible shield, the relentless solar wind would have long ago stripped the planet of its gaseous envelope, blowing its atmosphere into the icy void of space. Then our world would have become a lifeless desert, like Mars today, cold, dry, and dead. Meanwhile, in the deep, dark oceans, a hidden drama was unfolding. Imagine underwater hydrothermal vents, veritable geysers on the seafloor. Streams of scalding hot, mineral-rich water erupted from cracks in the Earth's crust. Rising from the seafloor, this water collided with the icy depths of the ocean. At these points of contact, seething cauldrons of energy emerged, zones of incredible chemical activity. It was here, to this source of warmth and food, that the first primitive microbes flocked. They created entire ecosystems that thrived not on sunlight, but on chemosynthesis. This astonishing survival strategy allows energy to be extracted not from light, but from chemical reactions. Just think, even today, in the darkest and most inaccessible corners of our planet, life thrives, using the same ancient methods inherited from those immemorial times when the world was very young and the sky above was not yet blue. Speaking of the sky, let's travel back 3 billion years and look up. We wouldn't see the usual blue sky. Early Earth's atmosphere was dense, saturated with methane, and almost devoid of oxygen. Because of this, the sky likely had a hazy orange or reddish hue. The land itself consisted of archipelagos of volcanic islands, constantly emerging from the boiling depths and sinking back into the ocean. The movement of tectonic plates, the very engine that drives the continents today, was only just beginning. Enormous underwater volcanoes seethed and hissed on the seafloor, spewing streams of heat and minerals directly into the dark waters of the primeval ocean. These geological formations are known as hydrothermal vents, or black and white smokers. Each was a kind of chemical reactor where scorching mineral-rich water collided with icy ocean water in a frantic dance. Many scientists today believe that it was in such harsh conditions in these underwater forges that life first took root. Imagine this scene: no forests, no grass, just rusty red waves crashing against the bare rocky shores. The ocean was a thick broth, saturated with iron, sulfur, and dissolved minerals. And somewhere in this ancient water, tiny organisms, archaebacteria, already lived. They swam, divided, and slowly, over millions of years, mastered the great secret of converting sunlight into energy. These were the distant ancestors of all photosynthetic life on the planet, and their home was this primordial toxic ocean. One of the greatest mysteries of this era is the so-called banded iron formations, geological layers found in ancient rocks around the world. These rhythmically alternating red and gray bands have long baffled geologists. A picture more reminiscent of Titan, Saturn's mysterious orange moon. This continued for a very long time until oxygen began to accumulate in the atmosphere. It was oxygen, like a great purifier, that dispersed this haze and gave our planet its famous blue color. This monumental transformation, which occurred billions of years ago, must have been an incredible sight. But at that moment, we're talking about the skies were still overcast, the oceans appeared rusty with dissolved iron, and life flickered only in the depths beneath the murky waters. The climate was also completely different. Our sun was young at that time and shone significantly less brightly than it does today. This fact gave rise to a scientific mystery known as the faint young sun paradox. Logically, with such a dim sun, our planet should have frozen solid, turning into an icy ball, locked in perpetual cold. However, geological evidence suggests otherwise. Ancient Earth had liquid water and a warm climate. How is this possible? The answer, as is often the case, lies in the atmosphere. A dense blanket of greenhouse gases, primarily methane and carbon dioxide, enveloped the planet, preventing heat from escaping into space. This powerful greenhouse effect more than compensated for the weakness of the young sun and created ideal conditions for the development of life. Remarkably, this saving balance was achieved thanks to life itself. Microorganisms produced methane, which altered the chemistry of the atmosphere and literally shaped the air the planet breathed. Earth transformed into a gigantic self-regulating mechanism where life had already begun to dictate its rules to the world around it. But despite all these miracles, the delicate balance could be upset at any moment. The planet remained extremely vulnerable. Even the slightest change in gas balance, a sudden movement of tectonic plates, or a new wave of meteorite bombardment could have catastrophic consequences. And yet, the late heavy bombardment era geologically speaking, ended only recently. This was a period when thousands of asteroids struck the young planets of the solar system with alarming regularity. Some scientists believe it was this cosmic barrage that delivered key components for life, such as water and phosphorus, to Earth. Others wonder how any living thing could have survived this cosmic cataclysm. But life endured. Against all odds, it clung to existence in quiet, shallow pools, in microscopic crevices of ancient rocks, in the chemical symphonies of underwater geysers. Wherever there was the slightest chance, life continued its great work, developing and evolving. It survived, adapted, and forever changed the chemical makeup of its world, laying the foundation for the entire grandiose future that awaited it. Over time, these microscopic pioneers began to fill the atmosphere with oxygen. For them, this gas was merely a byproduct, a waste product of their life processes. But for future, more complex organisms, it would become the elixir of life, a source of incredible energy. This transition, of course, would not be smooth. It would trigger the greatest extinction in history, a true ecological catastrophe that would completely change the rules of the game on the planet. But all this is yet to come. And now the Earth stands on the threshold of a great transformation. The air is thick with potential. The oceans churn with life forms never before seen. And the Earth itself, rich in resources and rocked by tectonic forces, is preparing to become the stage for the greatest drama in history. Slowly but surely, complexity is emerging. Breath is appearing. Creatures are emerging that will one day, billions of years from now, ask themselves, what was this world like in the beginning? We don't just live on Earth. We are part of its endless history. And this chapter, written 3 billion years ago, is not about kings and empires. It is a story of chemistry, patience, and invisible change. The next time you pick up an ordinary stone, just consider this. It could be older than any bone, older than any leaf on a tree. Perhaps it was formed in the very era when the sky was crimson, the sea rusty, and life took its first tentative steps. This is how the gigantic layers of banded iron ores that we find today were formed. The world's oceans were like a giant sponge, greedily absorbing every molecule of new gas. But every resource is finite, and one day, all the free iron in the ocean was bound up. The sponge filled to the brim. At that very moment, everything changed. With nowhere else to go, oxygen began seeping out of the water and into the air. Slowly at first, then faster and faster. And when that happened, the chemical balance of the entire planet was disrupted forever. At first, oxygen concentrations were negligible, less than 1% of today's levels. But even this was enough to turn the world upside down. Most of the microbes thriving in that ancient oxygen-free environment were anaerobes. For them, oxygen wasn't just a foreign element. It was a deadly poison. And now this poison was everywhere. Many scientists are convinced that this event caused the very first mass extinction in Earth's history. It wasn't a flash, an asteroid impact, or a volcanic eruption. It was a slow, inexorable chemical suffocation that stretched over millions of years. The atmosphere changed its color and composition. Ocean chemistry morphed. Ancient metabolic pathways that had been the key to success for 1 billion years became obsolete overnight. For organisms that couldn't adapt to the new rules, the only fate was extinction. However, despite all its destructive power, oxygen also opened up new, incredible possibilities. In its presence, cells were able to master an entirely new type of metabolism, aerobic respiration. This process proved to be an order of magnitude more efficient than all previously existing anaerobic methods. Aerobic respiration allowed for the extraction of tens of times more energy from the same glucose molecule. It was an evolutionary leap, comparable to the transition from the feeble flame of a candle to the power of a nuclear reactor. All the conditions were created for the emergence of larger and more complex life forms. But this didn't happen immediately. Evolution never hurries. It took hundreds of millions of years before life could fully utilize this incredible gift. The first wave of oxygen brought chaos and death, but over time, Earth began to find a new equilibrium. However, oxygen wasn't the only player in this drama. As its atmospheric levels rose, methane levels apparently fell. Yet it was this potent greenhouse gas that had warmed the planet under the rays of the dim young sun. Oxygen reacted vigorously with methane, converting it into carbon dioxide and water. And while CO2 is also a greenhouse gas, it's nowhere near as effective at trapping heat as methane. The planetary thermostat was broken. As a result, global temperatures began to plummet. Many scientists speculate that this was the trigger for one of the first and most severe ice ages in Earth's history. Glaciers began advancing from the poles, and at that time, they likely reached as far as the equator. The planet may have been almost completely covered in ice, turning into a giant snowball. What a cruel irony. The gas we today associate with life, fire, and warmth nearly plunged the entire world into an ice coma. We find evidence of these events in glacial deposits found in tropical latitudes, as well as in sharp fluctuations in carbon isotopes in ancient rocks. Imagine this scene: endless, blindingly white ice fields, ice kilometers thick, encases the oceans, reflecting the meager sunlight back into space. Only the peaks of the tallest volcanoes protrude from the ice, like frozen black islands in a white sea of silence. Icy silence enveloped a world that was only just learning to breathe in a new way. But Earth, as we already know, always finds a way to break free from its icy shackles. But even beneath this icy crust, the planet was not dead. Imagine, deep beneath the ice, volcanoes continued to erupt. The fiery heart of the Earth had not cooled. With each eruption, gigantic volumes of carbon dioxide were released into the atmosphere, and there was no one to absorb this gas. The oceans were frozen, and they could no longer dissolve it in their waters. Microscopic life capable of processing carbon died out or retreated into the depths. The gas simply accumulated year after year, century after century. Millions of years later, the planet began to slowly warm from within. The icy shell began to recede, and the ancient cycle of life began anew. This grandiose interplay of oxygen, methane, and carbon dioxide governed by the laws of temperature was the true heartbeat of ancient Earth. The slow, sometimes chaotic pulse of our planet's climate system was determined not only by the radiance of the distant sun or the trajectory of its orbit. It was set by tiny microbes and silent minerals. And at the very center of this cosmic drama, the invisible work of great evolution unfolded. It was in this new oxygen-rich world that one of the greatest evolutionary breakthroughs occurred. Eukaryotic cells emerged. They were no longer just primitive sacks of chemicals. No, Each such organism resembled a tiny but incredibly complex city, with its own districts and infrastructure, including a nucleus and specialized organelles. They became the foundation for all future, far more complex life forms. These evolutionary pioneers were far more efficient and possessed far greater potential for diversity than their simpler predecessors, prokaryotic cells. How did these living megacities emerge? The most compelling theory is that it's the result of an ancient alliance called endosymbiosis. Imagine this. One primitive cell attempted to devour another, but instead of becoming dinner, the prey survived within the predator. And instead of eternal war, they forged a pact of cooperation. It was no longer a duel between predator and prey, but the birth of a mutually beneficial partnership. Over time, these internal residents, once independent bacteria, evolved into vital organelles such as mitochondria, our energy plants, and chloroplasts, responsible for photosynthesis. This incredible process wasn't instantaneous. It was the result of a long chain of astonishing coincidences that, when combined, gave rise to a powerful new branch on the tree of life. A branch that eons later would lead to the emergence of algae, fungi, animals, and ultimately us. However, the key that turned the lock and opened the door to this new future was oxygen, one of the greatest paradoxes in the history of our planet. This gas, which became a deadly poison for countless ancient organisms, simultaneously laid the foundation for all future diversity. It acted as a great cleaner. By destroying the old, it made room for the new. This was not a one-time event, but a global tectonic shift, upsetting the fragile balance in a gigantic experiment that has been ongoing on our planet for billions of years. Evidence of this great drama is everywhere. It's sealed within rock masses, in ancient banded ironstones, and glacial deposits found even near the equator. It's hidden in the chemical composition of ancient sediments and in sulfur isotopes that bear the imprint of the oxygen revolution. It's preserved in biomarkers, molecular ghosts of once living cells. Today, researchers in every corner of the planet, from icy Greenland to the scorching deserts of South Africa and Western Australia, are digging into the Earth's oldest rocks. Using geological hammers and drills, they analyze the remnants of ancient oceans that dried up long before the first plants emerged onto dry land, and what they find tells the story of a natural transition, a story that continues to this day. It was a turning point in Earth's history, a milestone that marked not only destruction, but also great transformation. The Great Oxidation Event didn't just change the rules of life, it transformed the very face of the planet. Iron-bearing rocks gave way to red strata. Sedimentary rocks colored by iron oxides could only form in an oxygen-rich world. The very color of the Earth's surface changed. What was once gray and black literally rusted. The planet oxidized, taking on the hue of the breath of long-extinct microbes. It could be said that our entire world turned red thanks to bacteria. The oxygenation of the atmosphere, global glaciations, and the emergence of complex cells were merely the prologue. The greatest dramas in Earth's history were yet to come. But here, approximately 2.4 billion years ago, the rules of the game changed forever. Oxygen had become a permanent part of history, and now all life, for better or worse, had to adapt to it. Why was the entire planet covered in these iron-rich deposits, forming such regular patterns? The answer lies in one of the earliest and most monumental revolutions in the history of life. The fact is, the oceans of early Earth were literally saturated with dissolved iron. It floated freely in the water in enormous quantities. But then real revolutionaries arrived on the scene. Ancient bacteria that learned to use sunlight to generate energy. They didn't just passively bask in the sun like a modern plant on a windowsill. They actively converted its energy into food, and in the process, they released a byproduct, a new gas, oxygen, into the environment. Today, oxygen is the basis of our life. We breathe it. But 3 billion years ago, it was a deadly poison. Its appearance was a true shock to the entire planetary system. This highly reactive gas began to react with iron dissolved in the oceans, literally causing it to rust. As a result, oxidized iron precipitated and settled in thick layers on the seafloor. Over millions of years, this cycle repeated itself. A burst of bacterial activity, a release of oxygen, rusting of the oceans, and the formation of a layer of iron oxide. This is how these stripes appeared. The red layers are the rust, and the gray ones represent periods when oxygen was less abundant. What we see today is the geological record, evidence of Earth's first biochemical uprising. The Great Oxidation was a turning point, as if the planet were taking a deep breath after an unbearably long period of silence. However, this breathing did not immediately become steady, and the ensuing silence proved deceptive. Yes, Earth now had oxygen, but there was no sign of stability or balance. Instead, global backlashes began, and on a planetary scale, this always leads to catastrophe. The atmosphere, suddenly enriched with oxygen, set off a chain reaction. Each link in this chain seemed insignificant, but together they had colossal significance. Methane, a powerful greenhouse gas that once warmed the Earth under the light of the dim young sun, began to rapidly decay. It simply couldn't coexist with the corrosive oxygen, and as soon as methane levels plummeted, the planet began to cool. This wasn't a gradual cooling, it was the beginning of an ice age. There is compelling evidence that shortly after the first oxygen surge, the planet experienced one of the most extreme climate events in its history. Global glaciation was so extensive that the oceans may have frozen from the poles to the equator. Our planet became a giant snowball. The ice cap may not have been perfectly smooth. Some scientists believe there may have been pockets of open water trapped among the vast ice near the equator. But imagine for a moment this world, Earth completely covered in glaciers, hundreds of meters thick. The planet, once shrouded in a warm methane haze, now sparkled with an icy whiteness. The oceans became white fields, and the air froze in silence. The sun only dimly illuminated a world bound by eternal cold. And this state didn't last just one winter or even a single decade. It lasted for millions of years. It wasn't a quick freeze followed by a thaw, but a protracted planetary coma. By some estimates, ice may have covered the Earth for tens of millions of years, leading to the near-total collapse of photosynthesis. The surface oceans were blocked from sunlight. Shallow waters plunged into darkness, and life was once again forced to retreat to the depths, to where warmth and food could still be found, to hydrothermal vents and underground salt pockets. And yet, Earth didn't remain an icy wasteland forever. Why? because volcanoes never sleep. Even beneath the frozen sky, the boiling mantle continued to spew heat and gases to the surface. Volcanoes, oblivious to climate catastrophes, continued to pump carbon dioxide into the atmosphere, and since neither forests nor plankton could absorb it, this gas accumulated slowly but inexorably, like steam in a sealed boiler. Eventually, the greenhouse effect kicked in, but it manifested not as a trickle of warmth, but as a powerful, all-consuming flood. Temperatures soared. Glaciers began to melt, retreating like a gigantic tide, revealing the face of the planet. And when the oceans opened to the sun again, when the skies cleared a little, life surged forward once more. It was no longer the same life as before, and the chemistry of the world had changed, but it was still life. We can see echoes of this great transition in the isotopes preserved in rocks: carbon, sulfur, rubidium, iron. All of them carry subtle traces that tell us about changes in oxygen levels, ocean acidity, and global temperature. This whisper of the elements, locked in ancient stones, serves as a time machine for us. The echoes of events that played out billions of years ago still resonate in our world, and they speak to us not of chaos but of interaction. Earth isn't just a stage for the drama called life, it's an active participant. This inextricable connection between living organisms and the atmosphere, between rock and water, is what makes our planet so unique. Other worlds may also have volcanoes and even oceans, but it's precisely this delicate balance between biology and geology that has made Earth our home. After the first great oxygen wave, oxygen levels continued to rise, but less rapidly. This occurred in spurts, short bursts, and long periods of decline, followed by new sudden increases. It would be over 1 billion years before oxygen levels reached even a fraction of today's levels. And all this time, life continued to experiment. Cells became increasingly diverse. Some retained their ancient anaerobic habits, hiding from the toxic gas. Others learned to use oxygen to their advantage. To survive in the new conditions, some organisms grew larger and more complex, while others learned to cooperate. One of the greatest inventions of this era was symbiosis, and not just between individual cells, but between life itself and its environment. Consider again the emergence of eukaryotes, complex cells with internal architecture. Their emergence didn't just change biology. It expanded its capabilities to unimaginable limits. These new cells had nuclei to securely store and protect DNA. Within them, mitochondria, descendants of independent bacteria, worked, generating energy in exchange for safe haven. These new life forms possessed flexibility, complex structure, and enormous potential. Gradually, they began to diverge, dividing into evolutionary lineages that billions of years later would give rise to fungi, plants, and animals. But at that moment, in the quiet period that followed planetary chaos, they were still microscopic creatures floating in oceans where oxygen was still very scarce. About 1.8 billion years ago, oxygen levels stabilized again, but never reached their current levels. For hundreds of millions of years, they fluctuated around a few percent of their current concentration. Scientists sometimes call this strange evolutionary pause the boring billion. It was a period in Earth's history when, at first glance, almost nothing changed. Evolution seemed to slow down. Oxygen levels stagnated, and the climate cooled and stabilized. Compared to the turbulent catastrophes that occurred before and after, this period seems incredibly calm and quiet. But calling it boring would be a mistake. After all, behind this apparent calm lay preparations for the next great act in the drama of earthly life. But while the oxygen revolution subsided, the planet itself was not asleep. It continued to refine its great invisible processes. Imagine, mountains that had stood for centuries were slowly, grain by grain, eroded by wind and rain. This rock dust, rich in phosphorus and other vital elements, was carried by rivers into the world's oceans, nourishing their depths. The great carbon cycle in nature worked like a well-oiled machine. And in this apparent silence, in microscopic worlds, genetic diversity accumulated like a hidden force preparing to break through. There, in the shadow of humble microbial mats, a new revolutionary idea of life was born: multicellularity. This was no longer just a random accumulation of cells. It was the beginning of a true society, where each cell assumed its role, where labor was divided and specialization became the key to survival. We see the first hints of tissue, primitive organs, and complex structures. Life was not standing still. It was accumulating strength for the great achievements to come. At the same time, deep beneath us, in the planet's scorching heart, immense forces were awakening. The geological record bears traces of monumental tectonic upheavals. Vast landmasses, supercontinents, converged in titanic collisions and then broke apart again, like cracked ice. One such giant, Rodinia, witnessed continents drift across the face of the planet, altering ocean currents beyond recognition, reshaping climate maps and channeling nutrient flows along new routes. Mountain ranges rose skyward only to be ground to dust by the inexorable force of time. Rivers, like chisels, cut their way through stone, carrying the fragments of eras into the abyss of the seas. It was a vast feedback system on a planetary scale, and all the while, the oxygen waited patiently. It was still there. It merely paused, perhaps hindered by a lack of nutrients or the delicate balance between those who produced it and those who consumed it. Every burst of photosynthesis in one corner of the world triggered a response elsewhere, maintaining the precarious equilibrium of planetary chemistry. But this calm couldn't last forever. And then, approximately 600 million years ago, in the twilight of the Proterozoic era, something changed again. The frozen equilibrium was disrupted. Oxygen levels, that invisible architect of the future, began to creep upward again. At first slowly, almost imperceptibly, and then more and more rapidly. This second oxygen wave, which scientists sometimes call the Neoproterozoic Oxygen Event, opened the door to a burgeoning of animal life. What triggered it? We still don't know for sure. Perhaps it was tectonics, which delivered a new rich supply of fertilizer to the oceans. Or perhaps the very metabolism of microorganisms changed. Or perhaps it was simply time. The slow, centuries-long accumulation of genetic, geological, and chemical potential finally reached its tipping point. Whatever the cause, the result was stunning. An entirely new chapter in the history of life on Earth began. The planet, once again, became a world in turmoil. For the second time in its history, atmospheric oxygen levels began to rise rapidly. This set the stage for the emergence of entirely new, astonishing actors. It gave the green light for the emergence of the strangest creatures Earth had ever seen, the Ediacaran biota. Imagine an underwater world populated not by fish or crabs, but by living quilts, disc-shaped creatures, and mysterious spirals hovering in the water column. Their fossilized remains are found today all over the world, in Namibia, Newfoundland, and Australia. These creatures weren't yet animals as we understand them. They had no skeletons, no jaws, not even clearly defined heads. But they were large, complex, and multicellular, the first clear evidence that life had advanced from simplicity to complexity. And all of this was only possible thanks to oxygen. However, as before, he was not the only player in this field. The planet's carbon cycle also entered a phase of vigorous activity, triggering sharp and dramatic climate fluctuations. This may have been the beginning of a new, unstable era in the development of life. A wave of powerful glaciation swept across the planet, likely caused by the same rise in oxygen levels. The ice returned, encasing the world, and life was forced to retreat to the few remaining refugees. And once again, this strange planetary feedback played a role. Earth, having survived the Ice Age, was reborn. But this time, everything was different. The world became more than just breathable. It became incredibly dynamic. The era of complex life had begun. The first ecosystems, food chains, and symbiotic relationships began to form. Everything became intertwined into a single, complex network. Cells were no longer solitary wanderers in the ocean. They learned to build bodies, form tissues, and form colonies. They learned to sense light and move purposefully. And when millions of years later the Cambrian explosion struck, it didn't just appear out of nowhere. It brought with it eyes, shells, limbs, and the first true predators. But the foundation for this had been laid long before, in the deep, slow, oxygen-rich currents of Earth's Middle Age. When we look at this grand saga of our time, it seems almost like a myth, a creation legend. It is the story of the emergence of a molecule that created our skies, frozen the oceans, destroyed the old world, and sowed the seeds of a new one. It is the story of a gas that became both the elixir of life and a deadly poison. A molecule that was both breath and a sharp blade. Today, we take oxygen for granted, forgetting that our planet's past was anything but peaceful and stable. Such is the nature of global change. It doesn't always happen explosively. Sometimes it creeps up quietly over millions of years. Sometimes it poisons the world, and sometimes it transforms it beyond recognition. Oxygen was neither hero nor villain in this drama. It simply was. And life, incredibly tenacious, flexible, and forever seeking new paths, simply found a way to coexist with it. It either adapted or perished trying. And when Earth changes, it rarely does so gently. It stumbles, falls, is thrown from one extreme to the other, like a giant pendulum swinging through a shifting cosmos. And when oxygen burst onto the scene, the entire planetary system was set in motion. The Great Oxidation Event wasn't like the flip of a switch. It wasn't some clear line on the timeline dividing history into before and after. No, it was a chaotic, excruciatingly long and uneven process, stretching across entire geological eons. For hundreds of millions of years, the world changed, sometimes slowly and smoothly, sometimes in sudden leaps. But it could never reverse itself, and this change brought with it an avalanche of consequences. The first consequence was chemical. Oxygen, released from its watery cradle and pouring into the atmosphere, was not idle. It was incredibly active. It reacted with everything it could reach. The entire surface of the planet, all its exposed rocks and minerals, encountering this aggressive gas for the first time, literally began to rust. This process triggered a chain reaction of weathering in rocks that had not known such exposure for billions of years. The old chemistry of the Earth's surface died, and a new one was born in its place. The planet was covered in rust. But far more dramatic events were unfolding in the ocean depths. There, in the dark layers of water, an invisible war was already raging, a war of molecules and metabolisms. As oxygen seeped into the upper layers of the ocean, it created sharp chemical boundaries. In the sunlit shallows, breathing became easier, but the depths remained a dead, oxygen-free zone. Sulfur, methane, and dissolved iron still reigned supreme. The world's oceans became a kind of layer cake of death. On top lay a thin, oxygen-rich layer, an oasis for new life. And beneath it lay bottomless, dark depths, where sulfur, methane, and iron still reigned, a toxic world of the past trapped beneath a thin film of an oxygen-rich future. This created zones of fierce chemical competition. Bacteria, which had thrived for billions of years in an oxygen-free world, found themselves trapped. They were pushed deeper and deeper into tiny, isolated niches. Some adapted, others evolved, but most simply vanished. Their metabolic pathways, once dominant across the planet, were now relics of a bygone era. And then sulfur entered the picture. Most likely, cyanobacteria were behind this, tiny blue-green organisms that, without realizing it, began to shape our planet's future atmosphere. Of course, they had no grand plan. They didn't aim to make the air breathable for future creatures. Their only goal was to survive. But in the process of surviving, they initiated a massive process of terraforming the planet. And they did this not with complex machines, but simply with biochemistry and a vast amount of time. In those distant times, Earth didn't yet have the ozone layer that today protects us from the sun's harsh ultraviolet radiation. Because of this, the planet's surface was a death trap. Therefore, most living organisms hid in the water column. They found refuge in shallow waters, forming dense underwater carpets, or hiding under a thin layer of mineral sediment. These microbial communities, layered and slimy, adhered to rocks in the intertidal zone, gradually creating the amazing dome-shaped structures we know as stromatolites. The most astonishing thing is that stromatolites still exist today. In unique places like Shark Bay in Australia, you can see their living colonies, bubbly rock-like mounds that seem to preserve the memory of an ancient era. They are alive, and within them still live the descendants of those very same cyanobacteria. They continue their slow, unnoticed work, unaware that they are living fossils, witnesses to events so ancient that our minds can barely comprehend them. In this new chemical environment, some bacteria discovered a new way to survive. They began producing hydrogen sulfide. This gas smells like rotten eggs today. But back then, in the Proterozoic seas, it wasn't just an unpleasant odor. It was the smell of death itself. These sulfide-producing microbes thrived in the oxygen-free depths. As they multiplied, they released tons of hydrogen sulfide into the ocean. Catastrophic events occurred from time to time. This toxic gas would escape and enter the atmosphere. This phenomenon is called oxinia, a condition in which water is simultaneously deprived of oxygen and supersaturated with toxic sulfides. Hydrogen sulfide is a deadly poison for most forms of aerobic life. It inhibits protein function and destroys cell membranes. In high concentrations, it can suffocate even the most resilient organisms. Worse still, it destroys the ozone layer in the upper atmosphere, stripping the planet of its protective shield from harsh ultraviolet radiation. As a result of these events, Earth became not only chemically fragmented, but also deadly toxic. We still see the legacy of those times today in the form of black shales, sedimentary rocks rich in organic matter that formed in those very same oxygen-free toxic conditions. These rocks are more than just fossils. They are the frozen breath of ancient microbes, evidence of an era of toxic seas. Their consequences weren't limited to the ocean. As atmospheric oxygen increased, the concentration of methane, the era's primary greenhouse gas, began to decline. Methane traps heat tens of times more effectively than carbon dioxide. When oxygen began oxidizing it, converting it into the much less efficient CO2 and water, the planetary thermostat shifted sharply. The result was a global freeze. It is possible that this event triggered one of the most massive glaciations in history, the Huronian glaciation. When oxygen displaced methane from the atmosphere, the greenhouse effect weakened, global temperatures plummeted, and ice began its advance from the poles toward the equator. Tropical seas, once teeming with microbial life, turned to icy mush. Before us unfolds a stunning example of how everything on our planet is interconnected. Microscopic creatures change the composition of the atmosphere. The atmosphere changes the climate. The climate changes the conditions on the planet, and these conditions in turn decide which species live and which die. Species then change the chemistry of the world around them. It's an eternal dance of life, chemistry, and geology, repeating itself over and over again, and there's a dark elegance to this mesmerizing cyclicality. Despite all these cataclysms, life survived. Not everywhere, and not without enormous losses, but it persevered and continued on its way. Many anaerobic organisms for whom oxygen was a deadly poison were forced to flee. They sought refuge in isolated pockets of the Old World, in deep seabed sediments, in hot springs, far from the deadly breath of the new era. There, in these toxic enclaves, they became true masters of survival, extremophiles, living echoes of that ancient era. Other life forms, however, took up the fight. They followed the path of evolution, developing entirely new biochemical weapons, unique proteins and enzymes capable of neutralizing the destructive effects of oxygen. And today, billions of years later, their direct descendants still inhabit our planet. Consider, for example, the bacteria that still find refuge in the oxygen-deprived depths. They thrive in black smokers on the ocean floor or in underground aquatic reservoirs hidden from the world. These tiny creatures are silent guardians of the memory of that ancient earth, while the world above was irreversibly changing, becoming saturated with oxygen. This event opened the door to previously unimagined evolutionary opportunities. After all, with the advent of oxygen, a new type of metabolism emerged, oxidative. Imagine switching from wood to nuclear fuel. It was a colossal leap in energy efficiency. Cells could now obtain much more energy, allowing them to grow, become more complex, and support far more intricate internal processes. Of course, this metabolic breakthrough didn't happen overnight. It was the result of an incredibly long period of trial and error, a series of random mutations and ruthless natural selection. But the effort was worth it. The culmination of this long journey was the birth of an entirely new type of cell, eukaryotes. Unlike their primitive prokaryotic ancestors, they possessed a true command center, the nucleus, as well as a complex internal structure and set of organelles. The very first of these eukaryotes were likely microscopic solitaries, living in microbial mats or drifting through the water column as part of plankton. But they already harbored incredible potential. Their modular structure, flexibility, and capacity for complex transformations were completely unattainable by more primitive life forms. The emergence of the eukaryotic cell was, without exaggeration, one of the turning points in the history of all life on Earth. And while oxygen wasn't the sole factor initiating this process, it undoubtedly played a decisive role. Without this new energy source, it would have been simply unthinkable to meet the energy demands of such complex cellular machines. However, as often happens in the great drama of life, everything has two sides. On the one hand, oxygen became a catalyst for the development of more complex organisms, and on the other, it set off a chain of irreversible and global changes that transformed the face of the entire planet. The Earth's surface began to change before our very eyes. Minerals reacted with oxygen, rocks were subjected to a new type of erosion, and rivers carried an entirely new set of chemical elements into the oceans: phosphorus, molybdenum, heavy metals. All these substances dissolved in water began to have a powerful impact on marine ecosystems. The world's oceans have also been transformed. Their color, their chemical composition, even their smell have changed. Whereas the waters of the ancient seas once had a greenish tint due to the vast amount of dissolved iron, they now sparkle with new colors, filled with fresh chemical compounds. And like paleontological detectives, we can observe this great transition in the geological record. Before us unfolds a picture of layers of banded iron ores gradually giving way to so-called red beds. Rocks on the continents, speckled with patches of oxidized iron, become silent witnesses to this global transformation. Imagine the entire planet slowly turning crimson and rusty. And the artist behind this gigantic painting wasn't some unknown artist, but billions of microscopic creatures that were forever altering the chemical composition of the atmosphere. Planetary rust is perhaps one of the most spectacular and visible proofs of how life, invisible to the eye, can, over time, reshape an entire world. But the atmosphere didn't become breathable instantly. For many millions of years, oxygen concentrations remained extremely low. Perhaps just 1 or 2% of the levels we're accustomed to today. This was too low for the emergence of animals, or even for fire to survive, but it was enough to tip the balance in favor of a new oxygen-rich world. Earth entered a long, strange twilight period. This was an intermediate state, when oxygen was already present in the atmosphere, but its amount fluctuated constantly. Life on the planet reached its peak complexity at the interface between the two worlds, where old anaerobic ecosystems and new oxygen-rich ones existed side by side in a delicate balance. This wasn't a scorched post-apocalyptic desert. No, it was more of a transition zone, a gigantic natural laboratory where evolution conducted its boldest experiments, giving birth to new forms of life. And in this laboratory, life began to explore previously unimagined developmental paths. Some microorganisms learned to form complex colonies, while others experimented with a diversity of forms and functions. Genetic complexity steadily increased, and perhaps this is when the ability for sexual reproduction emerged. The great gene shuffling that would one day lead to the emergence of the most incredible creatures had already begun. However, these first steps were slow and hesitant, and almost no traces of them remained in the fossil record. For a long, long time, the Earth once again sank into apparent tranquility, but beneath the surface of this calm, hidden mechanisms of change continued their relentless work. The carbon cycle was shifting. New forms of symbiosis and cooperation emerged, and the processes of rock weathering changed, altering the delivery of nutrients to the ocean. A complex feedback system, ticking like a clock since the planet's birth, was preparing the ground for the great upheavals to come. The planet would never be the same. It had shed its old skin and, with a blink, emerged a completely new face. The age of oxygen had arrived, but like any new era, its beginning was marked by conflict. Oxygen wasn't just a passive gas that had taken its place in the atmosphere. It was an active, aggressive reagent that violently interacted with everything around it. Oxygen altered the chemistry of the world, transforming its appearance and rebuilding the established order at every level. The biosphere responded to these changes slowly and in a very unique way, not with an explosion of instant innovation, but with myriad small, careful experiments. Some of these led life into an evolutionary dead end, while others opened the way to incredible future discoveries. The Earth, as a geological body, was not left untouched. The Great Oxidation Revolution triggered a chain reaction of transformations within the planet's interior. Minerals that had remained stable for millions of years began to dissolve under the influence of active oxidative weathering on a planetary scale. Soils became more vibrant and dynamic. Rivers carried a new chemical cocktail to the sea, metals, phosphates, and clays, creating the very nutrient-rich broth in which new forms of life arose. And iron, that ancient ruler of the oceans, was also drawn into this cycle. Iron, which once floated freely in seawater in colossal quantities, was now trapped. Oxygen bound it, forced it to precipitate, and forever removed it from the water. Today, the gigantic iron ore deposits that fuel our civilization, providing steel for bridges, ships, and satellites, are nothing more than the legacy of those ancient processes. The consequences for marine ecosystems were catastrophic. Many of the ocean's first inhabitants were perfectly adapted to a world rich in iron and almost completely lacking oxygen. They relied on a chemistry that was now irrevocably lost. Some organisms were forced to migrate deeper, seeking refuge in anoxic layers where oxygen had not yet penetrated. Others were able to adapt, learning to utilize new chemical elements or to withstand the toxicity of oxygen. And some simply died out, unable to withstand the changes. But there, in the shallows, in a film-thin strip of oxygen-saturated water at the surface, new life began to bubble. This was the birth of so-called oxygen oases, local zones where the old and new worlds collided in a deadly yet simultaneously creative battle. In these zones, the composition of microbial communities began to rapidly change. Cyanobacteria assumed a dominant position, forming entirely new ecosystems. It was like a dress rehearsal for modern natural communities, only played out on a microscopic scale. And the consequences of this process continued to snowball. Changing ocean chemistry made trace elements such as molybdenum, zinc, and copper more available. These metals proved vital for the complex enzymes responsible for key cellular functions. And with them, new metabolic horizons opened. Life began experimenting not only with respiration, but also with cell growth, division, and coordination. Oxygen didn't just allow cells to grow larger. It paved the way for the creation of more sophisticated biological structures. Biochemical specialization emerged. Cells became more complex not only for their own survival, but also to interact with one another. As a result, multicellular organisms emerged on the scene, and this wasn't a miracle, but the natural result of a long series of random events. Nevertheless, the world remained frighteningly unstable. The atmosphere was constantly changing, fluctuating between calm and stormy. Oxygen levels would rise, creating conditions favorable for aerobic life, only to plummet again, poisoned by emissions of hydrogen sulfide or methane. These were turbulent, jagged periods lasting millions of years. One of the main culprits of this instability was the sulfur cycle. As oxidative weathering on land saturated the oceans with sulfates, sulfate-reducing bacteria began to thrive. These microbes, in the process of their activity, produced toxic hydrogen sulfide. This hellish mixture of oxygen and sulfides turned vast tracts of the ocean into veritable chemical kill zones. These dark episodes left their mark on sedimentary rocks in the form of anomalous sulfur isotopes. These strange ratios, like fingerprints at a crime scene, tell us that the world wasn't simply saturated with oxygen. It reacted to it in complex, violent, and often hostile ways. There's even evidence that at certain points, hydrogen sulfide may have been released into the atmosphere in enormous quantities. In high concentrations, this gas can destroy the ozone layer, which in turn would have allowed deadly ultraviolet radiation to reach the planet's surface. For early life on Earth, this would have been a real catastrophe. Perhaps this is why multicellularity remained a secondary, risky survival strategy for so long. And yet, life clung to existence in the most remote corners, in places where conditions were too harsh to completely eradicate it. And even amid these global crises, the seeds of cooperation and complexity began to sprout. Eukaryotic cells became increasingly common, and the fossil record, though scant in finds from that era, begins to show us the first signs of the emergence of larger, more complex structures. However, it's important to remember that oxygen wasn't the only thing that shaped this ancient world. Methane also played a key role. This powerful greenhouse gas was an integral part of the early Earth's climate, acting like a giant blanket, trapping heat on the planet in the dim, young sun. The first microbial communities emerged long before our planet's atmosphere was filled with life-giving oxygen. These ancient fossils have given science much more than mere facts. They have made the invisible visible, as if revealing the faces of long-gone eras on the tarnished mirror of time. And the more such fossil evidence has emerged, the deeper we have delved into our understanding of the evolution of our world. Let's travel to Australia's Turri Creek Basin. Here, in the depths of ancient rocks, scientists have discovered a veritable geological diary, the pages of which reveal a great transition from a world suffocated in an oxygen-free environment to a planet with a clean, oxygen-rich atmosphere. And this wasn't just a thin layer, but an entire rock record capturing a tectonic shift in the very history of life. Researchers like Kurt Kohnhauser dedicated themselves to studying how microbial civilizations responded to this global shift. They advanced a bold hypothesis. The iron and phosphorus cycles acted as the invisible orchestrator that guided the formation of the early biosphere. Imagine those first, barely noticeable glimmers of life. Were they colonies of independent cells? Or perhaps the first primitive tissues, the first attempts by an organism to become something more than the sum of its parts? It's impossible to say with certainty, but the vector of development was already set. And into this great drama, the planet itself intervened. Earth's climate began to change dramatically. Massive chemical processes were taking place in the atmosphere. Methane was oxidized, enormous masses of carbon were preserved in organic rock on the seafloor, and the concentration of carbon dioxide, the planet's warm blanket, steadily declined. The result was immediate. Global cooling set in. The Huronian glaciation was the first, but far from the last act of this icy drama. Later, in the Proterozoic era, our planet experienced at least 3 colossal ice ages, each more merciless than the last. These weren't just harsh winters. They were a true planetary hibernation. A blanket of ice encased even the equatorial latitudes. Gigantic glaciers creaked across the mountain peaks, and what had once been the tropics was buried under kilometers of snow. But in the ringing silence that followed each such global freeze, oxygen began to seep back into the atmosphere. As the Earth turned into an ice ball, photosynthesis almost completely stopped. This meant that volcanoes, which continued to erupt, were free to pump carbon dioxide into the atmosphere. The greenhouse effect grew like an invisible furnace, and eventually the ice began to retreat. And then, starved but hardened by trials, photosynthetic life returned with renewed vigor. Each freeze-thaw cycle was a brutal lesson, a dress rehearsal for future ups and downs. It was a true test of endurance for the entire biosphere. By the end of these turbulent eras, life had transformed beyond recognition. Cells became more complex and numerous. Their genetic code acquired unprecedented flexibility, and their energy production methods became more diverse. But the most fundamental change occurred at the level of interaction. True multicellularity emerged. It was in the harsh conditions of these glacial periods that the first truly complex organisms emerged. They were slow, lacking shells or claws, and unable to hunt, but they were remarkably well organized. Around 600 million years ago, the so-called Ediacaran biota blossomed in the oceans, marking a quiet but momentous revolution. These strange creatures, like living carpets, simply lay on the seafloor, absorbing nutrients directly from the water. Their flat, soft bodies left intricate imprints in the mud, fragile and rare evidence of their existence. Today, These fossils are priceless relics, genuine and unique messages from the past. They tell us of a completely new world, a world where oxygen ceased to be a deadly poison and became a life-giving environment, a fuel for evolution. An entire planet filled with limitless possibilities for development. Biology ceased to be simply a struggle for survival and became a creative force, setting off chain reactions that forever changed the face of the oceans, the atmosphere, the rocks, and even the genes themselves. In this great upheaval, old forms of life were swept away, giving way to new incredible possibilities. Space was created not only for survival, but also for complexity, for the emergence of structure, and very soon this structure will transform into movement, into complex behavior, into ecosystems of astonishing depth. But that's another story entirely for another day, because here, at the end of this era, Earth has changed. It hasn't healed or perished, it has become different. It is a breathing planet, where both storms and calms are now created by life itself. Ancient stones are forever stained with the waste products of microscopic cells too tiny to be seen. The skies cleared not by magic, but by merciless chemistry. The oceans, having tasted rust and poison, still found a way to propel life forward. The Great Oxygenation Event. It was not just a turning point, but the proclamation of a new law. Life doesn't simply exist on Earth. It writes its history on the very body of the planet, molecule by molecule. The Great Oxygenation Catastrophe seems like an absolute beginning, the moment when the world turned upside down and the sky itself breathed its first full breath. But in reality, it was just one chapter in a much longer and more complex saga. By that point, Earth had already gone through countless cycles of creation and destruction, innovation and stagnation. Even 3 billion years ago, the saturation of the atmosphere with oxygen was not the beginning of change. It was merely part of an ancient rhythm that had been resonating for all eternity. To truly grasp the magnitude of this moment, we must look even further back, to a time before the atmosphere had changed, before iron had settled to the bottom of the oceans, even before the first cell took its first breath. At the very beginning of time, Earth was more than just a pale blue dot in space. It was a fierce, restless, and living world, formed from the dust of dead stars. The newborn Earth grew at an incredible rate in the depths of the early solar system, constantly colliding with other protoplanets and devouring asteroids. For millions of years, it was a molten ball shrouded in fire and eternal darkness. Its surface was too unstable for continents to form and too hot for oceans to exist. However, even in those distant fiery times, the foundations of the future were already being laid. Gradually, our world formed its first atmosphere. It likely consisted of hydrogen and helium, gases too light to be held by the planet's young gravity. A powerful solar wind blew them into space, giving way to a second atmosphere, born in the boiling depths of the Earth itself. Powerful volcanic eruptions spewed carbon dioxide, nitrogen, sulfur, and water vapor into the air. These weren't just random emissions, but the first signs of future stability. When the planet's surface finally cooled sufficiently, water vapor in the atmosphere began to condense and rain down on the ground. Imagine a storm that lasted thousands of years, millennia of incessant downpours shaped our planet's climate and atmosphere, creating a cradle for the origin of life, a great flood. The first oceans filled the gigantic depressions on the surface, leaving only young, still soft patches of land above water. And in these primordial oceans, under tremendous pressure around underwater volcanic vents and in zones of chemical contrasts, life arose. We don't know exactly how it happened. We may never know, but somewhere between 4 and 3.5 billion years ago, the first spark ignited on Earth. Life was simple, single-celled, and chemically completely unique. Perhaps it all began with RNA molecules, fatty membranes, and cycles of self-replicating compounds triggered by lightning strikes, heat, or contact with minerals. Whatever the case, it happened. From a geological perspective, it happened almost instantly, and it hasn't stopped since. 3.5 billion years ago, we find the first evidence, stromatolites. These are layered microbial mats that, by trapping sedimentary rock particles, form bizarre rock domes. We also find isotopic traces of carbon, clearly recycled by living organisms. These are only hints, indirect evidence, but they unmistakably indicate that life was already thriving on our planet. And this demonstrates the first great law of the universe here. Life appears rapidly as soon as the slightest opportunity presents itself. It can take many forms, huddling near hydrothermal vents or clinging to particles of clay, but it always finds a way to exist. Life is enterprising and inventive, and as soon as it appears, it immediately begins to remake the world around it. The second law is that the environment always fights back. In the early Archean period, life was chemically constrained. The atmosphere contained no oxygen, only gases emitted by volcanoes. Cells quickly adapted to these conditions, developing a metabolism based on sulfur, iron, or methane. However, they were extremely vulnerable, dependent on a delicate chemical balance and occupying tiny ecological niches. But then, with the development of photosynthesis, first perhaps in purple bacteria and then in other microbes, life became much more resilient and diverse. With the advent of cyanobacteria, the world changed forever. These unique organisms learned to harness the energy of sunlight to split water molecules and produce oxygen. Although this oxygen was initially completely absorbed by iron dissolved in the ocean, it was destined to radically alter the atmosphere itself. This was only the beginning of monumental changes. It was the first great catastrophe, the first mass extinction, and the first global transformation caused by life itself. But it was not the last. Earth's history is not a smooth ascent to perfection. It is a series of abrupt interruptions and global upheavals. The Great Oxygenation Event destroyed the Archean world, but it was itself interrupted by subsequent glaciations, climate cycles, and continental shifts. Afterward came a period that scientists once dubbed the Boring Billion. The name arose because evolution seemed to slow, oxygen levels dropped, and fossils became incredibly rare. But we now understand that this period was not boring, but a time of great stabilization. It was a planet taking a breather. It was building new systems and establishing connections between them. It was during this time that supercontinents began to form. One of the earliest, Rodinia, gathered vast tracts of land into a single landmass. Its formation and subsequent breakup had colossal consequences for the entire planet, altering ocean currents, weather patterns, and nutrient cycling. These tectonic movements directly influence the planet's chemistry, determining where and how oxygen would be produced and stored. And herein lies another fundamental law. Plate tectonics is a powerful internal engine that drives life on the surface. Without it, nutrients would remain locked in rocks. Mountains would neither grow nor collapse, and minerals would not travel from land to sea. Tectonics is a source of eternal renewal, and every new mountain range, every crack in the seafloor, leaves an indelible mark on the history of biology. Just as life shapes the atmosphere, geology shapes life. We can still observe the echoes of these ancient monumental processes today. Let's travel back into our planet's deep past. The event we call the oxygen catastrophe was not unique. Imagine Earth's history as a series of monumental cataclysms triggered by invisible gases in the atmosphere. Dramatic fluctuations in their concentrations have occurred more than once. Let's recall the Great Permian extinction. Carbon dioxide entered the picture then. Its emissions reached such monstrous proportions that they led to the extinction of 90% of all species on the planet. And in the Devonian period, changing oxygen levels in the world's oceans triggered the mass extinction of coral reefs and ancient fish species. Even today, in our era, we can observe echoes of these same processes. The entire history of the Earth is permeated by these repeating cycles, these thresholds followed by irreversible climate shifts. History does not repeat itself exactly, but its patterns can be observed again and again. Life is in perpetual motion. It evolves, inexorably changing the world around it, experiencing eras of prosperity and devastating declines. And then it adapts, rises from the ashes, and begins again. Imagine evolution as not a straight line leading from the past to the future. Rather, it is a gigantic, twisting spiral. Sometimes it soars upward, reaching new heights of complexity. Sometimes it spins in place, as if in disarray. And sometimes it plunges downward, collapsing all creation and forcing life to start its journey virtually from scratch. The Great Oxidation Event, seen from this perspective, is just one turn of this grandiose spiral. It was not unique in its destructive power, but its significance was fundamental. It set a precedent for all future global transformations. The very idea that microscopic life forms are capable of completely reshaping the geochemistry of an entire planet seems incredible, but it is a fact. And this realization is truly sobering. We are accustomed to thinking of life as something fragile, defenseless against the might of volcanoes or asteroid impacts. And for the most part, this is true. But sometimes life itself becomes an asteroid, a force that brings total extinction, and this happens not through malice or some mistake. No, it's simply because life has learned to survive too well, and in the process has altered its home too much. Oxygen was simply a byproduct of ancient microbes, and its accumulation in the atmosphere was never their goal. Nevertheless, the consequences were global. This gas changed the planet's temperature, the structure of the oceans, the mineral cycle, and ultimately sent evolution down an entirely new path. This event created winners and losers, completely rewriting the script for life on Earth. And this brings us to a deeper, more humbling idea. What if the true story of Earth isn't the story of individual species? Not the story of trilobites, dinosaurs, forests, or even you and me, What if it's the story of global feedback mechanisms that allow the planet to find equilibrium again and again? Imagine a system that allows one element to develop and thrive until it threatens the stability of the whole. Then the system cools it, reins it in, changes the rules of the game, not consciously, not by someone's will, but through some uncanny ability to self-correct. Oxygen levels rose, life flourished, then life collapsed, and ice encased the planet. Volcanoes warmed the world again, life returned, but more complex than before. These are cycles within cycles, intertwined stories. But there were other events, even earlier, less visible, but no less important. The invention of methanogenesis, when methane-producing microbes appeared on the planet, played a key role in warming the young Earth. The development of oxygenic photosynthesis, which occurred long before oxygen began to accumulate in the atmosphere, introduced entirely new strategies to the microbial competition for energy. With each passing year, scientific models became more precise and data became more plentiful. But the essence of this work remained unchanged. It still requires complete immersion in the silence of ancient rocks. The ability to ask questions in the language of chemical elements and patiently waiting for the earth to reveal yet another of its secrets. This kind of science requires a special mindset and incredible humility. The scale of research is colossal, and the questions it poses are completely absorbing. Imagine spending 10 years studying mineral deposits in a single region, only to find a sample on the other side of the world that turns all your conclusions upside down. You can devote decades to a single theory, sifting through mountains of scientific papers, analyzing, doubting, and pruning away the excess until only the pure kernel of truth remains. But even then, a single, more perfect sample from a drill hole can destroy a lifetime's work in an instant. And yet it seems none of these scientists ever give up. They keep returning to their work not because they crave definitive answers, but because they are completely in love with the process of searching itself, with the process of listening to poetry frozen in stone. Imagine teams of researchers setting out on an expedition to the Isua Greenstone Belt in Greenland. These ancient rocks, over 3.7 billion years old, are located in one of the most inaccessible places on the planet. Even the formation of the Earth's core and the birth of its magnetic field were absolutely necessary. It was this invisible shield that protected the early atmosphere from the destructive solar wind. Without these seemingly insignificant changes, the Great Oxidation Event would never have occurred. Without a magnetic field, all oxygen would have been swept into space. Without plate tectonics, nutrients would have remained forever locked in rock. Without oceans, photosynthesis would simply be meaningless. And without complex chemical, geological, and biological feedback loops, none of this would have mattered. Perhaps the most profound truth is that Earth is not just a rock hurtling through space. It is a complex system composed of countless interconnected parts. We can imagine it as a living organism on a planetary scale, not in a mystical, but in a purely scientific sense. Air influences water, water changes rock, and rock influences life. Life, in turn, changes the composition of the atmosphere, and this great cycle continues endlessly. Today, this idea is called the Gaia hypothesis, not as a deity, but as a concept that allows us to understand Earth as a single, living whole. And the Great Oxidation Event was the first real irrefutable proof of this concept. Life changed the planet, and the planet responded. When we imagine ourselves in those eras, looking at the icy worlds, the silent stromatolites, and the molten crust of ancient Earth, we see more than just a series of events. We see common themes: transformation, tension, the very passage of time, and through it all, the calm and inexorable flow of life. This is the broader context in which our planet has always been in constant flux. Disturbances are part of its normal functioning. Feedback and catastrophes are how the planet breathes. And even extinction, no matter how final it seems, is often only a prelude to the birth of something new and even more wondrous. And as we move forward to new discoveries, to new chapters in Earth's history, we carry this knowledge with us. The world we live in was not given to us. It was forged. Again and again, in fire and ice, in oxygen and silence, in light and darkness. In this chemical darkness of the ancient world, through the work of tiny cells, truly amazing things happened. The global cataclysms we see were just the tip of the iceberg. The main work was carried out slowly, imperceptibly, but relentlessly. And even now, billions of years later, we can see its results. We often imagine the distant past as something forever sealed in stone, inaccessible to all but time itself. But in reality, its traces are scattered all around us. We just need to know where to look and listen. Sometimes, it's a barely audible whisper, detectable only under a powerful microscope. Sometimes it's a jagged rocky outcrop in the middle of the desert, captivating with its unusual shape. And sometimes it's a thin reddish line of rock running along a high cliff. Most people would pass it by without noticing, but to the trained eye of a geologist, it tells a whole story. It's in these quiet, forgotten corners of the planet where nothing seems to happen that generations of scientists have dedicated their lives to extracting fragments of the past from the depths of the Earth. The story of how we came to understand a great oxidation event continues. The ancient world it transformed is more than just a tale of gases and minerals. This is a story about people. Curious, persistent, sometimes stubborn, often with weathered and tanned faces. About people who set out in search of something they didn't even have a name for yet. Take, for example, the vast, sun-baked expanses of the Pilbara region in Western Australia. Before us lies an ancient Craton, a land of scorching heat, sparse, thorny shrubs, and rocks that are among the oldest on the planet. And here, in this silence and emptiness, a true scientific revolution began. It occurred not in the rocks themselves, but in how we learn to read them. In the 1980s, a paleobiologist named William Schopf, peering through a microscope, saw tiny filamentary structures. They were embedded in silica, a fossilized rock, and they looked suspiciously like microbes. These specimens were found in the Apex Formation, estimated to be approximately 3.5 billion years old. At first, his claim sounded too bold to be believed. He claimed to have found the oldest known fossils of life on Earth, and not just any life forms, but photosynthetic bacteria, perhaps the distant ancestors of those very cyanobacteria that will one day fill the planet's atmosphere with oxygen. The ensuing debate was heated, furious, and at times personal. Some scientists welcomed the discovery with enthusiasm, but others expressed serious doubts. Were these filaments truly the remains of living organisms, or could they simply be the result of mineral growth, which sometimes mimics organic forms? The line between the living and non-living worlds is incredibly thin, especially when we're dealing with evidence so ancient that it predates most modern continents. Years passed, and scientific methods were refined. New studies utilize sophisticated technologies such as spectroscopy and isotope analysis. Scientists studied the enigmatic fossils from the Apex Formation again and again. Some results confirmed their biological origin, while others cast serious doubt on this hypothesis. Even today, these debates continue, reminding us that in science, mystery often outlasts definitive certainty. However, despite all the controversy, the apex fossils opened a new door for researchers. They proved that searching for traces of early life is not a hopeless endeavor. They showed that we must search in the harshest, most ancient, and most inhospitable corners of our world, and so the researchers continued their search. In South Africa's Barberton Greenstone Belt, they found even more clues: fossilized microbial mats, specific carbon isotope ratios, and banded iron ores were discovered there. These ancient rocks also told a story of a planet once teeming with iron-rich oceans and microbes already actively colonizing their world. In the search for answers to these questions, one name often comes up in the scientific community: Roger Buick, an astrobiologist and geologist. Buick's work has given us a completely new perspective on our planet at its dawn. He learned to read the writings left by time on rock, allowing us to better understand how the environment changed in that distant era. Chemical evidence of early photosynthesis has been discovered in the Isua Formation of Greenland and the Hamersley Basin of Australia. These were the first tentative signs that oxygen had already begun its slow but inexorable ascent, one day forever changing the face of the earth. It was a time when not only our understanding of life's impact on the planet itself changed. Perhaps the most incredible shock occurred in the minds of the explorers themselves. They learned to read rocks. Before them lay not simply frozen, silent boulders, but veritable multi-volume sagas. These were chronicles written in the language of iron, sulfur, carbon, and silicon. After all, to understand rock is to master the language of colossal pressure and endless time. Let's travel to the Timagami region of Canada. Imagine a drilling rig biting into ancient earth, bringing cores, cylindrical rock samples, to the surface. In them, scientists discovered deposits of unimaginable antiquity, oversaturated with iron. But the most astonishing thing was that this iron didn't lie in a continuous sheet. It was arranged in neat, rhythmic layers, creating what geologists call banded iron quartzites. For decades, the world's best minds have puzzled over this mystery. What unknown force caused iron to precipitate from ocean water in such perfectly even bands? What caused the world's oceans to periodically rust and then become crystal clear again? The answer didn't come overnight. It was built from bits of data accumulated over years. Only by the end of the 20th century did these fragments form a coherent model of how oxygen first appeared in the ancient oceans. At the very beginning of their existence, the Earth's vast expanses of water were, in essence, a gigantic iron solution. And then tiny microorganisms, the first photosynthetic organisms began releasing a new, revolutionary gas into the water: oxygen. It immediately reacted with the dissolved iron, triggering a monumental chemical process. Iron oxides, or rust, simply put, settled to the bottom, forming layer upon layer of these very same bands. These rhythmic layers of rust appear to reflect global fluctuations in oxygen levels. Perhaps they were due to seasonal blooms of microscopic bacteria, which would multiply rapidly and then die down. Or perhaps they were the result of slower, secular changes in the ocean currents that carried nutrients. This discovery forever changed our view of the past. The rock record didn't just confirm the existence of oxygen, it revealed how it transformed the ocean, creating the very geological formations that today serve as our window into the dawn of time. Around the same time, a new generation of scientists emerged. They were now preoccupied with deeper questions, not simply when did oxygen appear, but how rapidly did it accumulate? Was this process gradual or, conversely, chaotic and explosive? Did this event occur once, or was it a series of waves rolling across the planet? In search of answers to these questions, researchers turned to one of the most powerful tools in their arsenal: isotope geochemistry. By measuring the ratios of different isotopes, varieties of the same element with different numbers of neutrons, they learned to reconstruct detailed pictures of bygone eras. Sulfur isotopes proved particularly revealing. In a world devoid of oxygen, sulfur behaves in a unique way, undergoing unique chemical reactions and leaving behind a distinctive isotopic signature. However, as atmospheric oxygen levels rise, the rules of the game change, and this signature disappears. And then, approximately 2.45 billion years ago, this ancient sulfur signal suddenly vanished across the planet. A new one arose in its place: the chemical signature of a world whose atmosphere already contained free oxygen. This signal became a global marker, an indelible mark of the Great Oxidation Event, leaving its imprint on the rocks of every continent. It was a turning point in the Earth's autobiography written in stone, and it raised new questions. How exactly did oxygen emerge? Was it the work of cyanobacteria alone? Or perhaps plate tectonics played a role? And what if accumulated organic carbon prevented the oxygen from disappearing again? One of the most influential thinkers in this field was geochemist Donald Canfield. He proposed a completely new model for how the Earth became oxygenated early in its history. In the 1990s, he advanced a bold hypothesis. Even after oxygen appeared in the atmosphere, the ocean depths remained virtually lifeless and oxygen-free for a very long time. He believed that for more than 1 billion years, sulfides and iron, not oxygen, reigned supreme in the dark depths. This model, known as the Canfield Ocean, suggested that the chemical environment of early Earth was far more complex than we'd previously thought. The planet's oxygenation didn't occur smoothly and gradually, but in leaps and bounds, in agonizingly slow stages, with constant reversals. This process was full of dramatic highs, crushing lows, and astonishing intermediate states. Other researchers wove their own unique threads into this narrative. Timothy Lyons studied how rare trace elements like molybdenum and vanadium responded to oxygen levels, using them as indicators of ancient chemical conditions. Shuhai Xiao examined fossils of the first multicellular life, trying to understand what environmental changes might have triggered its emergence. And James Farquhar deepened our understanding of sulfur isotope anomalies and their role in early atmospheric chemistry. Their collaborative work created a veritable scientific symphony, unfolding in sterile laboratories, scorching deserts, glaciers, and the ocean floor, and everywhere the silent witnesses were the rocks, waiting and watching. Each time a new core was extracted, a new isotope analyzed, or a new microcosm image, another note was added to the music of Earth's deep past. While many of these discoveries were made in the laboratory, the most important breakthroughs occurred right out in the field. It was there that the most moving and dramatic moments unfolded. Imagine a graduate student somewhere in Greenland, knee-deep in snow, hammering a rock with a geological hammer. Little did he know that the tiny sample he was about to place in his backpack would later contain the isotopic signature of 3.8 billion-year-old life. Or imagine a geochemist trudging through the Namibian desert, sweltering in the heat, weighed down by water canisters, field journals, and fragile hope. Or a paleontologist dusting a flat stone and suddenly freezing, realizing that the pattern beneath his fingers is no random play of nature. It's cellular. These aren't scenes from a Hollywood movie. They're real, and they happen not through blind luck, but through steely persistence. Science, especially the science of things unimaginably ancient, isn't built solely on brilliant insights. It's founded on patience, on endless days in the field, on slow and painstaking data analysis, and on hypotheses that are tested and then die with dignity, giving way to new ones. Some questions continue to haunt us today. The history of the Great Oxidation Event remains full of mysteries and blank spots. Modern technologies, such as synchrotron imaging, isotope analysis, and computer modeling of biochemical processes, allow us to look at old puzzles from a completely new perspective. Perhaps we will soon have answers to the most important of them. Did oxygen levels rise suddenly like a tsunami, or did it occur gradually over millions of years? Was this event caused solely by biology, or did the movement of tectonic plates and the general cooling of the planet play a role? Could something similar happen again on other worlds, on other planets? And the central question is, what does all this mean for us?